Beneath the swirling clouds of Jupiter lies a world of wonders and mysteries. As the largest planet in our solar system, Jupiter is a dynamic and powerful force that has shaped the history of our cosmic neighborhood. From its mesmerizing great red spot to its deep metallic hydrogen core, Jupiter holds secrets that challenge our understanding of physics, chemistry, and astronomy. Hidden beneath its thick atmosphere are layers of unimaginable pressure and temperature, where storms rage with the power of 1,000 hurricanes. Its immense gravity orchestrates the movements of dozens of moons and protects the inner solar system from dangerous cosmic debris. Let's take a closer look, exploring both the science and the speculation that make this planet one of the most captivating subjects in our solar system. Why Jupiter's depths remain one of astronomy's greatest mysteries. Jupiter is a giant world with an aura of mystery that has intrigued humans for centuries. Its immense size and swirling clouds make it a standout object in the night sky. But what lies beneath those clouds is a question that remains largely unanswered. The depths of Jupiter are shrouded in secrecy, a realm where conventional exploration methods face insurmountable challenges. Decades have been spent attempting to unravel its secrets, yet many aspects of its interior remain unknown. The planet's upper layers are composed of ammonia clouds that form intricate patterns and vivid storms, including the iconic Great Red Spot. Beneath this chaotic surface lies a multi-layered structure of gases, which becomes increasingly opaque and impenetrable as one moves deeper. Unlike Earth, where solid landmasses and oceans provide reference points, Jupiter lacks a definitive surface. Its gaseous layers gradually transition into denser, hotter material, creating an environment that is difficult to model or explore. Telescopes, whether ground-based or space-based, can only capture light and radiation from the planet's uppermost layers. The deeper regions remain hidden, obscured by the same clouds that make Jupiter so visually striking. Instruments designed to measure light and heat struggle to pierce through the dense atmosphere. As one descends into the planet, the pressure rises to levels unimaginable on Earth. Even the strongest materials we know would be crushed under the weight of Jupiter's atmosphere at deeper levels. This pressure also generates extreme heat, creating an environment hostile to any equipment we could currently send there. The deeper regions of Jupiter are thought to reach temperatures of tens of thousands of degrees, with pressures so intense that hydrogen, the planet's primary component, transforms into a metallic state. The Juno spacecraft, currently orbiting the planet, has provided valuable data about its atmosphere, magnetic field, and gravitational pull. However, Juno cannot directly explore the deeper layers. Its instruments rely on indirect measurements, such as monitoring the planet's gravitational effects on the spacecraft itself. By analyzing these subtle shifts, scientists can infer the density and distribution of materials within Jupiter. But such methods only scratch the surface. Spacecrafts can also only operate for a finite period, as the harsh environment around Jupiter takes its toll on their systems. The planet's intense radiation belts, which are among the most powerful in the solar system, can damage electronics and limit the amount of time a spacecraft can remain operational. This makes it difficult to conduct longer-term studies. Future missions aim to overcome some of these barriers by employing innovative techniques. Proposals include spacecraft equipped with more advanced instruments, capable of withstanding the intense radiation and extreme conditions around Jupiter. Some researchers have even suggested the possibility of deploying probes that could penetrate the planet's atmosphere and send back data from within. Such missions would require significant advancements in materials science and engineering, as well as new ways of transmitting data through the dense and turbulent atmosphere. The secrets hidden in Jupiter's multicolored atmosphere. Jupiter's multicolored bands and swirling storms offer a visual display unlike anything found on Earth. Each layer of Jupiter's atmosphere holds clues about its internal workings, making it a critical area of study for scientists seeking to understand this gas giant. The alternating light and dark stripes, known as zones and belts, stretch across the planet's surface. Zones are lighter in color and are thought to consist of rising air currents, while belts are darker and contain descending air currents. This constant movement creates powerful jet streams, which flow at incredible speeds and help maintain the planet's striped pattern. These jet streams are much stronger than anything seen on Earth, with winds reaching speeds of hundreds of miles per hour. Scientists believe that the light zones are made of ammonia clouds that reflect sunlight, giving them their pale appearance. The darker belts, on the other hand, may contain compounds like sulfur and phosphorus, which are brought up from deeper layers and undergo chemical reactions in the upper atmosphere. These reactions produce the reddish and brownish hues that dominate the belts. The planet's upper layers are dominated by ammonia clouds, but as one moves deeper, the pressure and temperature rise dramatically. This creates layers of different chemical compositions, each influenced by the conditions at that depth. Below the ammonia clouds, scientists suspect there are layers of ammonium hydrosulfide clouds, followed by a region dominated by water clouds. However, these deeper layers remain largely unobserved. The planet's weather systems are dynamic and ever-changing, driven by internal heat as well as energy from the Sun. Jupiter emits more heat than it receives, a phenomenon linked to the slow release of energy trapped during its formation. This internal heat drives powerful convection currents, which carry gases and heat upward, fueling the storms and turbulence seen in the atmosphere. These processes are thought to play a major role in shaping the planet's banded structure and its weather patterns. One of the most iconic features of Jupiter's atmosphere is the Great Red Spot, a massive storm that has raged for centuries. This storm is larger than Earth and is located within one of the planet's belts. It rotates counterclockwise, with wind speeds reaching hundreds of miles per hour. The reddish color of the Great Red Spot is still a topic of debate, but some scientists believe it may be caused by chemicals brought to the surface and altered by sunlight. The distribution of elements like hydrogen and helium in the atmosphere can provide clues about the planet's formation and evolution. By analyzing the ratios of these elements, scientists can test theories about how Jupiter accumulated its mass and what role it played in shaping the early solar system. The atmosphere acts as a gateway to understanding the deeper layers, where materials transition from gaseous to liquid states under immense pressure. Juno's instruments can measure temperature, pressure, and chemical composition, allowing scientists to build detailed models of the planet's layers. One surprising finding from Juno is the discovery of ammonia concentrations that vary significantly across the atmosphere. This suggests that Jupiter's interior may have complex circulation patterns, with material moving between layers in ways that are not yet fully understood. Jupiter is often considered a prototype for similar planets found in other star systems. By learning more about its atmosphere and internal structure, scientists can refine their models of how gas giants form and evolve. This knowledge can then be applied to exoplanets, helping us interpret observations of distant worlds. Despite the progress made, many questions remain about Jupiter's atmosphere. For example, the exact mechanisms that drive its jet streams and maintain its banded appearance are still not fully understood. The interactions between different chemical compounds in the atmosphere, as well as the role of the planet's magnetic field in shaping its weather, are areas of ongoing research. These mysteries ensure that Jupiter will continue to be a focal point for astronomers and planetary scientists in the years to come. Ammonia and water ice, the puzzles of Jupiter's atmospheric chemistry. Ammonia is one of the most abundant compounds detected in Jupiter's atmosphere. It's found in the planet's upper layers, where it forms the pale clouds that dominate the zones. Ammonia freezes at very low temperatures, creating ice particles that reflect sunlight. But ammonia doesn't stay neatly confined to the upper layers. It is constantly being cycled through the atmosphere, carried by powerful convection currents that rise from the planet's deeper regions. These movements seem to form regions of high and low concentrations, especially near the equator. Earlier models of Jupiter's atmosphere assumed a more uniform distribution. The findings suggest that ammonia is being transported in complex ways, possibly linked to large-scale weather patterns or internal circulation within the planet. On Jupiter, ammonia interacts with other chemicals to create powerful atmospheric phenomena. Some storms are believed to involve ammonia ice mixing with water ice, producing lightning and other dramatic effects. These storms are massive in scale, spanning thousands of kilometers and lasting for extended periods. They play a significant role in redistributing heat and chemicals throughout the atmosphere, shaping the planet's overall climate. Water is thought to exist primarily in the deeper layers of the atmosphere, where higher pressures and temperatures allow it to form clouds. These water clouds are hidden beneath the ammonia and ammonium hydrosulfide layers, making them difficult to observe directly. However, indirect measurements from missions like Juno have provided evidence of their existence. Water is a powerful greenhouse gas capable of trapping heat and influencing atmospheric circulation. When water vapor rises and cools, it condenses into droplets or ice particles, releasing heat in the process. This heat release fuels convection currents, which carry materials upward and drive the formation of storms. The energy involved in these processes is immense, far greater than what is seen in Earth's atmosphere. One example of water's influence on Jupiter is the occurrence of massive lightning storms. These storms are thought to originate in the water cloud layer, where strong convection creates the conditions necessary for lightning to form. The lightning bolts on Jupiter release energy that can be detected from space. Scientists are still trying to determine the exact amount of water present on the planet. Early measurements from the Galileo probe suggested that Jupiter's atmosphere was drier than expected, but later, observations from Juno have hinted at higher water concentrations in certain regions. These conflicting results have sparked debates about the distribution of water on Jupiter and its implications for the planet's formation. Both ammonia and water are thought to originate in the planet's interior, brought to the surface by convection currents. Their presence in the atmosphere provides indirect evidence of what lies beneath the visible layers. Their interaction adds another layer of complexity to Jupiter's atmospheric chemistry. When these compounds mix, they can form new chemical species, such as ammonium hydroxide. These reactions are influenced by the extreme conditions in Jupiter's atmosphere, including high pressures and temperatures. Understanding these chemical interactions is crucial for building accurate models of the planet's atmosphere and predicting its behavior. What lies beneath? The transition zone between gas and liquid metal. Hydrogen is a simple and lightweight element, one that behaves predictably under normal conditions. In Jupiter's upper atmosphere, it exists as a gas, much like it does on Earth. But as you descend deeper into the planet, the environment changes dramatically. The pressure increases exponentially, and temperatures climb to thousands of degrees. At a certain point, these extreme conditions force hydrogen into a state where it no longer behaves like a gas. Instead, it becomes a liquid, and eventually transitions into a metallic state, capable of conducting electricity. The existence of metallic hydrogen was first predicted decades ago, but it remains a theoretical concept in many ways. Scientists believe that in this metallic form, hydrogen is densely packed, with its electrons free to move, much like the behavior of electrons in metals like copper or aluminum. This free movement of electrons makes metallic hydrogen an excellent conductor, a property that likely plays a crucial role in Jupiter's magnetic field. Metallic hydrogen is predicted to be a superconductor, meaning it can conduct electricity without resistance. If this property can be confirmed, it could have applications in fields ranging from energy transmission to magnetic levitation. However, these possibilities remain theoretical until metallic hydrogen can be reliably produced and studied on Earth. The transition zone, where hydrogen shifts from a molecular gas to a metallic liquid, is one of the most mysterious regions of Jupiter. This area is thought to lie thousands of kilometers below the visible clouds, at pressures millions of times greater than those at Earth's surface. The precise depth and nature of this transition remain uncertain because the conditions are impossible to replicate on Earth. Even the most advanced laboratory experiments can only approximate the extreme pressures and temperatures found in Jupiter's interior. The transition zone is not a sharp boundary, but a gradual change where hydrogen begins to exhibit properties of both a liquid and a metal. This duality makes it even harder to define and study. In this region, hydrogen molecules are thought to break apart under the immense pressure, releasing their electrons and forming a fluid that behaves like a liquid, but conducts electricity like a metal. This unique state of matter challenges traditional classifications and highlights the complexity of Jupiter's interior. Metallic hydrogen is believed to be the source of the planet's immense magnetic field, which is one of the strongest in the solar system. As Jupiter rotates, the metallic hydrogen layer likely acts as a giant dynamo, generating electric currents that produce the magnetic field. This process is similar to how Earth's core generates its magnetic field, but on a much larger scale. Jupiter's magnetic field is the largest and most powerful in the solar system, extending millions of kilometers into space. This field creates a protective bubble around the planet, known as the magnetosphere, which shields it from charged particles streaming from the Sun. The strength and scale of Jupiter's magnetic field have long puzzled scientists, as they far exceed what would be expected from a planet of its size. The transition zone may also help explain some of the observed phenomena in Jupiter's atmosphere. For instance, the heat generated by the transformation of hydrogen and the movement of materials in this region could drive convection currents that influence weather patterns and storms in the upper atmosphere. The existence of metallic hydrogen suggests that Jupiter's interior has been under extreme pressure for billions of years, a condition that likely began during the planet's formation. Understanding this transition could provide insights into how Jupiter accumulated its mass and how similar processes might occur in exoplanets beyond our solar system. Advances in computer modeling and high-pressure experiments have allowed scientists to simulate the conditions within Jupiter more accurately. These studies have confirmed some aspects of the metallic hydrogen theory while raising new questions about the precise nature of the transition and its implications for the planet's structure. How Jupiter's extreme pressures forge exotic states of matter. Jupiter's immense size and gravitational pull create pressures and temperatures unmatched anywhere else in the solar system. These extreme conditions forge materials into states that are not only unfamiliar, but entirely unique. The deeper one ventures into Jupiter's interior, the more the behavior of matter begins to defy what is known from experiments on Earth. At the surface, or more accurately the visible cloud tops, Jupiter's pressures are relatively low, comparable to conditions experienced in Earth's upper atmosphere. However, this changes rapidly with depth. Every kilometer of descent adds an overwhelming increase in pressure. The crushing force grows so immense that the basic structure of atoms and molecules begins to change. Materials that would behave predictably on Earth become unrecognizable under these conditions. One of the first transitions that matter undergoes in Jupiter's interior is the compression of gases into liquids. Unlike the clear distinction between gases and liquids on Earth, this boundary blurs under Jupiter's intense pressure. Hydrogen and helium, which dominate Jupiter's composition, are gradually compressed into a dense, fluid-like state. This state behaves like a liquid, but retains some properties of a gas, a phenomenon that challenges the conventional definitions of phases of matter. As the pressure exceeds millions of times that of Earth's atmosphere, hydrogen transitions into metallic hydrogen. Beyond metallic hydrogen, there are theories suggesting that Jupiter's core may host other exotic states of matter. The innermost regions of the planet are subjected to pressures and temperatures that are so extreme they might just give rise to forms of matter that have only been theorized. One possibility is the existence of superionic ice, a state of water where oxygen atoms form a solid lattice while hydrogen ions flow freely, creating a substance that behaves both as a solid and a liquid. Superionic ice is believed to exist in the interiors of ice giants like Uranus and Neptune, but some scientists speculate it might also be present in Jupiter's core, where water could be trapped and compressed. Another potential state of matter in Jupiter's interior is degenerate matter, a highly dense form that occurs when particles are packed so tightly that quantum mechanical effects dominate their behavior. Degenerate matter is more commonly associated with the cores of white dwarf stars, but it might exist in trace amounts within Jupiter's core if the pressures are high enough. This type of matter challenges the classical understanding of density and structure, as it resists further compression due to quantum effects rather than the repulsion between atoms. The high pressures and temperatures could force elements like carbon and nitrogen into unusual configurations, creating materials that are stable only under such extremes. Some researchers have suggested that carbon in Jupiter's interior might form into diamond-like structures, sinking through the planet's layers like glittering rain. Using tools like diamond anvil cells, researchers can compress small samples of material to pressures similar to those found in Jupiter's interior. These experiments have confirmed some aspects of metallic hydrogen and other exotic states, but they are limited in scope. The conditions in Jupiter's core are so extreme that they push the boundaries of what is possible, even in the most advanced laboratories. Could metallic hydrogen unlock new energy frontiers on Earth? If it could be created and stabilized under less extreme conditions, metallic hydrogen might revolutionize energy production and storage. Its unique properties, high conductivity, immense energy density, and potential as a superconductor, offer tantalizing possibilities for transforming the way humans generate and use power. In its compressed state, metallic hydrogen is believed to store an incredible amount of energy. This energy is a result of the intense pressure needed to force hydrogen atoms into a metallic state. If metallic hydrogen could be synthesized and then made stable at normal pressures, releasing the stored energy could provide an unprecedented amount of power. One of the most talked about applications of metallic hydrogen is as rocket fuel. Traditional chemical rockets rely on the combustion of fuel to generate thrust, but metallic hydrogen could potentially offer a far greater energy output per unit of mass. This could dramatically reduce the weight of rockets, making space travel more efficient and less costly. A rocket powered by metallic hydrogen might reach destinations in the solar system faster than ever before, opening up new possibilities for exploration and even colonization. The potential energy density of metallic hydrogen could make it the most powerful rocket propellant ever conceived, allowing for missions that are currently beyond the capabilities of existing technology. One of the greatest challenges in renewable energy is finding efficient ways to store power generated by sources like wind and solar. Current battery technologies, while improving, still face limitations in energy density and longevity. Metallic hydrogen, with its theoretical ability to store massive amounts of energy in a compact form, could provide a solution, making it a game changer for the global energy grid. Perhaps the application with the greatest potential is the use of metallic hydrogen as a superconductor. Since a superconductor is a material that conducts electricity without any resistance, that means no energy is lost as heat. Most superconductors only work at extremely low temperatures, requiring costly cooling systems. However, metallic hydrogen is theorized to be a room temperature superconductor, meaning it could function without the need for cooling. If this property were realized, it could revolutionize industries dependent on electrical power. Electrical grids could transmit power over vast distances without any loss, dramatically improving efficiency. Magnetic levitation systems, such as those used in high-speed trains, could become more practical and widespread. The development of room temperature superconductors could also lead to breakthroughs in quantum computing, medical imaging, and other cutting-edge technologies. On Jupiter, the pressures needed to create metallic hydrogen are naturally provided by the planet's immense gravity, which compresses hydrogen to pressures exceeding 4 million times the atmospheric pressure on Earth. Reproducing these conditions in a laboratory is no small feat. Even when metallic hydrogen is produced, it is typically unstable, reverting to its gaseous form as soon as the pressure is released. To harness its potential, researchers would need to find a way to stabilize it at normal pressures. This would involve not only creating metallic hydrogen, but also keeping it in its metallic state outside of the extreme conditions required for its formation. Some scientists speculate that certain chemical or physical processes might make this possible, but so far, these ideas remain theoretical. Even if metallic hydrogen could be stabilized, creating it in quantities large enough for practical use would require enormous energy inputs and advanced technology. The infrastructure needed to produce and store metallic hydrogen would likely be costly and complex, at least in the early stages of development. However, many transformative technologies, from electricity to nuclear power, faced similar hurdles during their initial development. If it were used as a rocket fuel or energy source, the release of its stored energy would need to be carefully controlled. An uncontrolled reaction could result in catastrophic explosions, posing safety challenges. Additionally, the environmental impact of producing and using metallic hydrogen on a large scale would need to be studied to ensure that it does not create new problems while solving others. The Great Red Spot, a storm that refuses to die. The Great Red Spot is one of the most recognizable features of Jupiter, a colossal storm that has raged for centuries, if not longer. It is so large that it could easily swallow Earth whole. Yet its longevity and behavior continue to puzzle scientists. While storms on Earth tend to dissipate after days or weeks, the Great Red Spot has persisted for nearly 200 years, based on telescopic observations. Its resilience is unlike anything seen in Earth's weather systems, raising questions about the forces driving and sustaining it. The storm is an anticyclone, meaning it rotates counterclockwise in Jupiter's southern hemisphere. Unlike hurricanes on Earth, which draw energy from warm ocean waters and eventually weaken when they move over land or cooler regions, the Great Red Spot is fueled by Jupiter's turbulent atmosphere. Jupiter has no solid surface to disrupt the storm, and its immense size allows it to draw energy from the powerful jet streams that encircle the planet. These jet streams flow in alternating bands of eastward and westward winds, creating a dynamic environment where storms can grow to extraordinary proportions. At its largest recorded size, it spanned nearly 40,000 kilometers in diameter, large enough to fit 3 Earths side by side. Today, the storm has shrunk to about 16,000 kilometers across, yet it remains a dominant feature of Jupiter's atmosphere. The reasons for its gradual shrinking are not fully understood, but scientists believe it may be related to changes in the surrounding jet streams or the loss of energy over time. Despite its shrinking size, the storm remains remarkably stable, maintaining its shape and distinctive red coloration. The red color of the storm is thought to be caused by chemicals in Jupiter's atmosphere reacting with sunlight, but the exact composition of these chemicals is not known. Some theories suggest that the color comes from complex organic molecules, while others propose that it may be due to sulfur compounds. Hurricanes on our planet are driven by the heat released from water vapor condensing into rain, a process that cannot occur on Jupiter due to the lack of liquid water on its surface. Instead, the Great Red Spot is powered by the immense heat rising from Jupiter's interior, which creates powerful convection currents. These currents lift gases from deep within the planet, mixing them with the upper atmosphere and sustaining the storm's energy. On Earth, hurricanes lose energy when they encounter land, as the friction and lack of warm water disrupt their structure. Jupiter, being a gas giant, has no land masses. Instead, the storm moves slowly within its band of jet streams, interacting with other atmospheric features, but never encountering a surface that could weaken it. Some scientists believe that the storm could eventually dissipate entirely, while others argue that it may stabilize at a smaller size. Observations have shown that the storm occasionally sheds parts of its outer edges, creating smaller vortices that drift away and merge with the surrounding atmosphere. These shedding events may be a natural process that helps the storm maintain its stability over time. On Earth, the most powerful storms are limited by the size of the planet and the availability of energy sources like warm oceans. Jupiter, with its massive size and internal heat, provides an environment where storms can grow to scales unimaginable on Earth. The Great Red Spot is a testament to the extreme conditions on Jupiter and the complexities of its atmospheric dynamics. Studying the Great Red Spot has also provided insights into the behavior of other storms on Jupiter. Smaller storms, some of which are also long-lived, dot the planet's atmosphere and interact with the jet streams in fascinating ways. These interactions can sometimes result in storms, merging or splitting, creating a dynamic and ever-changing atmospheric landscape. By understanding the Great Red Spot, scientists hope to uncover broader principles about the behavior of storms on gas giants and other planets. The deep roots of the Great Red Spot, probing its subsurface origins. The longevity of Jupiter's giant storm has led scientists to theorize that the storm must be fueled by energy sources deep within the planet. Unlike Earth, where weather is primarily driven by solar heating, Jupiter generates a significant amount of internal heat. This heat, left over from the planet's formation and ongoing slow contraction, rises from the deep layers of the atmosphere and interacts with the storm systems above. The Great Red Spot is thought to tap into this internal energy, allowing it to sustain its violent winds and turbulent motion. Juno has provided some of the most detailed data yet about the storm's structure. Early findings suggest that the Great Red Spot is far more than a surface phenomenon. Instead, its roots extend deep into the atmosphere, possibly as far as 300 kilometers below the visible clouds. This depth is astonishing when compared to storms on Earth, which are confined to a relatively thin layer of the atmosphere. The Great Red Spot is shaped by powerful jet streams that flank its edges, creating a stable environment where the storm can persist. These jet streams, which flow in opposite directions, act like barriers that prevent the storm from dissipating or drifting across the planet. However, they also add to the storm's complexity by introducing turbulence and waves that interact with its structure. One of the key tools for studying the Great Red Spot's depth is microwave radiometry. This technique allows scientists to measure the temperature and composition of the atmosphere at different depths. Data from Juno's microwave radiometer has revealed that the storm's temperature varies significantly with altitude. The upper layers of the Great Red Spot are cooler than the surrounding atmosphere, while the deeper layers are warmer. This temperature gradient is thought to drive the storm's powerful updrafts and downdrafts, creating the swirling motion that defines its appearance. The storm is made up of gases like hydrogen, helium, ammonia, and water vapor. But the exact proportions and interactions of these elements are still not fully understood. The reddish hues are believed to be caused by sunlight and high-energy particles. However, the deeper layers of the storm may contain different chemical compositions, thanks to protection from sunlight, along with the immense pressures and temperatures within Jupiter's atmosphere. The pressures within the Great Red Spot increase dramatically with depth, reaching levels that are difficult to replicate in laboratory settings. As the pressure rises, hydrogen begins to transition, creating unique conditions that may influence the storm's behavior. This transition zone between gas and liquid hydrogen is a frontier of planetary science. The depth of the Great Red Spot also raises questions about its interaction with Jupiter's magnetic field. The planet's strong magnetic field extends far into space and is influenced by the movement of charged particles in the atmosphere. As the Great Red Spot churns, it may generate electrical currents that interact with the magnetic field, creating subtle effects that extend beyond the atmosphere. Jupiter's polar cyclones. Why do they form geometric patterns? The poles of Jupiter present one of the most visually striking features in the solar system: enormous cyclones arranged in geometric patterns. Unlike the swirling storms on Earth, these polar cyclones form configurations that are symmetrical and surprisingly stable. At the North Pole, 8 massive cyclones encircle a central one, creating an octagonal shape. At the South Pole, a similar pattern emerges, with 6 cyclones forming a hexagonal arrangement around a central storm. These formations have baffled scientists since they were first observed by the Juno spacecraft. The cyclones themselves are colossal in scale. Each one spans thousands of kilometers across, comparable to the size of continents on Earth. They rotate in a counterclockwise direction in the northern hemisphere and clockwise in the southern hemisphere, consistent with the Coriolis effect caused by Jupiter's rapid rotation. The winds within these cyclones can reach speeds of several hundred kilometers per hour, making them some of the most powerful storms in the solar system. Despite their intensity, these cyclones maintain their positions relative to one another, showing a level of stability that is difficult to explain. Unlike Earth, where weather is primarily driven by energy from the Sun, Jupiter generates a significant amount of heat from within. This internal heat is the result of the planet's gradual contraction over billions of years, which releases energy in the form of heat. This process, known as Kelvin-Helmholtz contraction, provides a constant source of energy that drives atmospheric circulation and creates the conditions for these massive storms. The absence of surface friction allows cyclones to persist for long periods, and the interaction between cyclones on Jupiter's poles creates a balance of forces that prevents them from merging or drifting apart. This balance is thought to be governed by a combination of atmospheric dynamics, including the Coriolis effect, centrifugal forces, and pressure gradients. Computer simulations suggest that the cyclones are surrounded by strong jet streams that act as barriers, preventing them from merging with one another. The jet streams create a stable environment where the cyclones can maintain their positions while rotating around the central storm. The exact mechanisms behind the formation of these jet streams and their role in maintaining the geometric patterns are still under investigation. Another factor that may contribute to their stability is the depth of Jupiter's atmosphere. This vertical structure may help anchor the cyclones, preventing them from drifting away or dissipating. The interaction between the deep atmospheric layers and the upper layers could create a dynamic system that stabilizes the cyclones and their geometric arrangement. The geometric patterns observed at Jupiter's poles are not entirely unique in the solar system. Saturn, for example, has a hexagonal feature at its north pole, but it is a single jet stream rather than a series of cyclones. The differences between the polar features of Jupiter and Saturn highlight the complexity of gas giant atmospheres and the role of planetary characteristics in shaping atmospheric phenomena. Jupiter's larger size, greater internal heat, and faster rotation may contribute to the formation of its distinctive polar cyclones and their geometric patterns. The stability of these cyclonic patterns raises questions about the energy sources that sustain them. On Earth, storms are fueled by heat from the sun and dissipate as they lose energy. On Jupiter, the combination of internal heat and the planet's rapid rotation creates a self-sustaining system where cyclones can persist for years or even decades. The energy driving these storms is immense, and understanding how it is distributed and maintained within Jupiter's atmosphere is a key area of research. Juno's instruments can measure the temperature, wind speeds, and chemical composition of the storms, revealing details about their dynamics and interactions. Data from Juno's microwave radiometer suggests that the cyclones have warm cores, with temperatures increasing toward the center of each storm. This temperature gradient may play a role in sustaining the cyclones and their geometric arrangement. The presence of the various gases in the cyclones can provide clues about the processes occurring within the storms and the deeper layers of Jupiter's atmosphere. For example, variations in the concentration of ammonia within the cyclones could indicate upwelling of material from the planet's interior, driven by the heat and dynamics of the storms. Mysteries of Jupiter's jet streams, rivers of wind in the sky. Jupiter's jet streams are these rivers of wind that streak across the planet, forming the iconic bands of color that define Jupiter's appearance. Unlike the jet streams on Earth, which are limited to a few distinct paths in each hemisphere, Jupiter's jet streams are numerous and span nearly the entire planet. They alternate in direction, with some flowing eastward and others westward, creating a striking pattern that shapes the planet's weather and storms. The jet streams on Jupiter are much faster than those on Earth, with wind speeds reaching up to 600 kilometers per hour in some regions. These powerful winds carve the atmosphere into bands known as zones and belts. The lighter zones are regions of rising air, while the darker belts are areas where air sinks back toward the planet. This continuous movement of air creates a dynamic system where energy is constantly exchanged, driving the complex weather patterns observed on Jupiter. Jupiter rotates once every 10 hours, a much faster rate than Earth. This rapid rotation generates strong Coriolis forces, which influence the movement of air and help establish the alternating pattern of the jet streams. The planet's large size means that these forces operate on a much grander scale than on Earth, allowing the jet streams to stretch across thousands of kilometers. Jupiter's internal heat drives convection in the atmosphere, causing warm gases to rise and cooler gases to sink. As these gases move, they are deflected by the Coriolis forces, giving rise to the jet streams. Despite the turbulence and chaotic weather on the planet, the jet streams maintain their structure over long periods of time, probably due to the deep roots of the jet streams which extend far below the visible clouds. The jet streams act as boundaries between different atmospheric regions, influencing the formation and movement of storms. The Great Red Spot, for example, is confined within a band of jet streams that help sustain its rotation and prevent it from drifting across the planet. Smaller storms and vortices are similarly affected by the jet streams, which can either merge them into larger systems or tear them apart. Jupiter's magnetic field interacts with charged particles in the atmosphere to create auroras and other phenomena. The movement of these particles is influenced by the jet streams, which can carry them across the planet and shape their distribution. This interplay between the jet streams and the magnetic field highlights the interconnected nature of Jupiter's atmospheric and internal processes. Studying Jupiter's jet streams has also provided insights into atmospheric dynamics on other planets. Saturn, for instance, has a similar banded appearance, suggesting that its jet streams operate in a comparable way. Even on Earth, the principles observed on Jupiter can help scientists better understand the behavior of jet streams and their impact on weather and climate. The scale and intensity of Jupiter's jet streams make it helpful for studying these phenomena in a way that would be impossible on Earth. The dynamo beneath: how Jupiter's core powers its magnetic field. Jupiter's magnetic field stretches millions of kilometers into space, enveloping the planet and its moons in an invisible shield of magnetism. This magnetosphere is so vast that if it were visible, it would appear larger than the sun in the sky. At its heart lies a dynamo, a process driven by the planet's internal structure and composition. Understanding this dynamo requires delving deep into Jupiter's core. The strength of Jupiter's magnetic field is about 20,000 times greater than Earth's. It is produced by the movement of electrically conductive metallic hydrogen deep within the planet, which generates magnetic fields as it moves and swirls within the planet. Jupiter's immense size and gravitational pull compress its interior to extraordinary levels. Under these conditions, the metallic hydrogen circulates, driven by the planet's rotation and internal heat, creating powerful electric currents. These currents, in turn, produce Jupiter's magnetic field. The rapid rotation of Jupiter plays a critical role in the dynamo. The planet completes a full rotation in just under 10 hours, despite being more than 11 times the diameter of Earth. This fast rotation causes the interior to churn with incredible energy, driving the movement of metallic hydrogen and amplifying the magnetic field. The interaction between rotation and convection creates a dynamic environment where magnetic fields can grow and evolve. While the metallic hydrogen layer is thought to be the primary driver of Jupiter's magnetic field, the planet's core also plays a role. The core is believed to be a dense mixture of rock, metal, and hydrogen compounds, though its exact composition remains uncertain. Some models suggest the core may be partially dissolved, blending with the surrounding metallic hydrogen layer. This blending could create additional currents and contribute to the complexity of the magnetic field. However, because Jupiter's core is hidden beneath thousands of kilometers of dense atmosphere, studying it directly is a challenge. Juno's magnetometers have mapped the field in unprecedented detail, revealing that it is not uniform. Instead, it has regions of varying strength and polarity, including an unusual area near the equator known as the Great Blue Spot. This feature, a localized patch of intense magnetic activity, suggests that the dynamo processes within Jupiter are more complicated than previously thought. The discovery of such variations has prompted scientists to rethink their models of how magnetic fields are generated on gas giants. The interaction between Jupiter's magnetic field and its surrounding environment creates a dynamic system that extends far beyond the planet itself. The magnetosphere captures charged particles from the solar wind and traps them in radiation belts that encircle the planet. These belts, similar to Earth's Van Allen belts, but much more intense, pose significant challenges for spacecraft and instruments operating near Jupiter. The magnetic field also interacts with the planet's moons, particularly Io, which is the most volcanically active body in the solar system. Io's volcanic eruptions release vast amounts of material into space, creating a plasma torus that is shaped and controlled by Jupiter's magnetosphere. The auroras at Jupiter's poles are another striking manifestation of its magnetic field. These auroras, the brightest in the solar system, are caused by charged particles spiraling along magnetic field lines and colliding with atoms in the upper atmosphere. Unlike Earth's auroras, which are primarily driven by the solar wind, Jupiter's auroras are largely powered by the planet's own rotation and the interaction between its magnetic field and Io's plasma torus. These auroras provide a visible link to the powerful dynamo at work beneath Jupiter's surface. Scientists are still trying to determine how the field has evolved over time. Jupiter's magnetic field is thought to have been active for billions of years, but its current configuration may not be the same as it was in the past. Studying changes in the field could provide clues about the planet's interior and the processes that sustain the dynamo. Many gas giants, both in our solar system and in distant star systems, are thought to have similar dynamos powered by metallic hydrogen or other conductive materials. By studying Jupiter, scientists can gain insights into the magnetic fields of these distant worlds and the role they play in shaping planetary systems. Additionally, the principles of the dynamo process are not limited to planets. They also apply to stars, including our Sun, which generates its magnetic field through similar mechanisms involving ionized gases. Auroras beyond imagination, Jupiter's polar light show. The auroras at Jupiter's poles are unlike anything else in the solar system. They are immense, dynamic, and vibrant, stretching thousands of kilometers across and glowing in hues of ultraviolet and infrared. These displays of light are far more powerful than the auroras on Earth, a reflection of Jupiter's immense size and the strength of its magnetic field. Auroras occur when charged particles, such as electrons and ions, interact with a planet's magnetic field and atmosphere. On Jupiter, the process begins deep in the planet's magnetosphere, where particles are accelerated along magnetic field lines toward the poles. As these particles collide with molecules in Jupiter's upper atmosphere, they release energy in the form of light. The result is a stunning and ever-changing light show that can be seen even from space. The planet's magnetic field, being the strongest, captures vast numbers of charged particles. These particles come from several sources, including the solar wind and the volcanic activity on Io, one of Jupiter's largest moons. Io plays a particularly important role in shaping Jupiter's auroras. The moon's surface is dotted with active volcanoes that release sulfur and other materials into space. These materials form a torus or ring of plasma around Jupiter, which becomes trapped in the planet's magnetic field. As Io orbits Jupiter, it generates powerful electrical currents through a process called electromagnetic induction. The interaction between Io's motion, Jupiter's rotation, and the planet's magnetic field creates a circuit of energy that flows along magnetic field lines to the poles. This energy is then released in the form of auroras. The connection between Io and Jupiter's auroras is so strong that a bright spot, known as the Io footprint, appears in the auroras, marking the moon's position in its orbit. Unlike Earth's solar wind-driven auroras, Jupiter's auroras are largely powered by the planet's rapid rotation. Jupiter's incredible rotational speed creates a continuous and powerful flow of energy that sustains the auroras, even when solar activity is low. Observations from spacecraft and telescopes have revealed that Jupiter's auroras are incredibly dynamic. They flicker, brighten, and shift in response to changes in the magnetosphere. For example, when the solar wind intensifies, it compresses Jupiter's magnetosphere, causing a surge of energy that lights up the auroras. Similarly, volcanic eruptions on Io can inject fresh material into the plasma torus, altering the aurora's intensity and structure. These interactions create a constantly changing display that reflects the complex and interconnected systems at work around Jupiter. The colors of Jupiter's auroras are another area of interest. While Earth's auroras are typically green and red, caused by the excitation of oxygen and nitrogen in the atmosphere, Jupiter's auroras include shades of ultraviolet and infrared. These colors result from the unique composition of Jupiter's atmosphere, which is dominated by hydrogen. When charged particles collide with hydrogen molecules, they produce ultraviolet light, which is invisible to the human eye but can be detected by specialized instruments. Equipped with instruments designed to observe the planet's poles, Juno has provided detailed images and data on the aurora's structure and behavior. The spacecraft's ultraviolet imaging spectrograph and infrared spectrometer have captured stunning views of the auroras, revealing intricate patterns and movements. These observations have helped scientists understand the processes that drive the auroras and their connection to Jupiter's magnetic field. The interaction between Jupiter's magnetic field and its moons. Jupiter's magnetic field doesn't just shape the environment around the planet, it profoundly affects its moons, creating complex interactions that are both fascinating and unique in the solar system. The four largest moons of Jupiter, Io, Europa, Ganymede, and Callisto, each experience the influence of this powerful magnetic field differently, with Io, Europa, and Ganymede showing the most dramatic effects. Io sits closest to Jupiter and bears the brunt of the magnetic field's influence. The intense gravitational pull from Jupiter and its neighboring moons creates tidal forces that stretch and compress Io, heating its interior and fueling its volcanoes. These eruptions release vast amounts of sulfur and other gases into space, forming a torus of plasma around Jupiter. As Io moves through the plasma torus, it acts like an electrical conductor, creating a circuit that connects the Moon to Jupiter's poles. These currents, which can reach millions of amperes, are responsible for the bright auroral spots associated with Io that appear in Jupiter's polar regions. The magnetic connection between Io and Jupiter is so strong that it creates visible effects in both the Moon's environment and the planet's auroras. Europa, the icy moon thought to harbor a subsurface ocean, also experiences significant effects from Jupiter's magnetic field. As Europa orbits within the magnetosphere, the field induces electrical currents in the Moon's salty ocean, which conducts electricity. These currents interact with the magnetic field, creating distortions that have been detected by spacecraft. These observations provide indirect evidence of Europa's ocean and its potential for habitability. The magnetic field also influences Europa's thin atmosphere, which is primarily composed of oxygen. Charged particles from Jupiter's magnetosphere bombard Europa's surface, knocking molecules loose and contributing to the atmosphere. This process, known as sputtering, creates a dynamic interaction between the magnetosphere and the Moon's surface, constantly replenishing the tenuous atmosphere. Ganymede, the largest moon in the solar system, is unique in that it has its own magnetic field. This intrinsic field interacts with Jupiter's magnetosphere, creating a miniature magnetosphere around the Moon. The interaction between these two magnetic fields is complex and creates a region of magnetic turbulence. This turbulence has been studied by spacecraft like Galileo, which detected energetic particles and waves in the space around Ganymede. Ganymede's magnetic field also affects its atmosphere and surface. Like Europa, Ganymede has a thin atmosphere primarily composed of oxygen, and charged particles from Jupiter's magnetosphere contribute to its formation through sputtering. The Moon's magnetic field provides some protection from these particles, creating a kind of shield that reduces the intensity of the bombardment compared to Europa. The plasma interactions between Jupiter's magnetic field and its moons create some fascinating phenomena. For example, the movement of charged particles along magnetic field lines creates bright auroral emissions on the surfaces of Io and Europa. These emissions are visible as glowing spots that shift position as the moons orbit Jupiter. Ganymede's unique magnetosphere creates its own auroras, which have been observed as faint glows near the Moon's poles. Jupiter's magnetic field also influences the movement of charged particles within the magnetosphere, creating radiation belts that pose challenges for spacecraft and potential human exploration. These belts are particularly intense near Io's orbit, where the plasma torus adds to the density of charged particles. The radiation environment is so extreme that it can damage spacecraft electronics and instruments, requiring careful planning and shielding for missions studying the Jovian system. Understanding the interactions between Jupiter's magnetic field and its moons helps scientists plan missions to these moons, particularly Europa and Ganymede, which are prime targets for studying the potential for life beyond Earth. Spacecraft like the upcoming Europa Clipper and the European Space Agency's JUICE mission are designed to study these moons in detail, focusing on their magnetic and plasma environments to better understand their habitability. Io's volcanic fury, how Jupiter shapes its most active moon. Io is a volcanic powerhouse that seems almost alive with its constant eruptions and shifting landscapes. Its surface is a chaotic mix of molten lava, volcanic vents, and colorful sulfur deposits. Its position as the closest of Jupiter's major moons places it in a unique gravitational tug-of-war. Jupiter's immense gravity pulls strongly on Io, but the moon isn't orbiting alone. It is locked in a gravitational resonance with Europa and Ganymede, meaning their orbital periods are in a precise ratio. This resonance causes Io's orbit to be slightly elliptical, rather than perfectly circular. As Io moves closer to and farther from Jupiter during its orbit, the varying gravitational pull stretches and compresses the moon. This process, known as tidal heating, generates enormous amounts of internal heat. The friction created by the constant flexing of Io's interior causes its rocks to melt, producing magma. Unlike Earth, where heat comes primarily from radioactive decay in the core, Io's heat is almost entirely due to this tidal interaction. The result is a moon that experiences near-continuous volcanic activity, with eruptions far more frequent and intense than anything on Earth. The scale of Io's volcanic activity is staggering. Lava fountains shoot up dozens of kilometers into the sky, and massive lava flows can cover areas larger than some countries. The temperatures of Io's lava are some of the highest recorded in the solar system, exceeding those of Earth's most active volcanoes. These eruptions reshape Io's surface on a regular basis, erasing impact craters and creating new landforms. This makes Io one of the youngest-looking surfaces in the solar system, despite being billions of years old. Io's volcanoes also release vast amounts of sulfur and sulfur dioxide gas, which contribute to its striking appearance. The moon's surface is covered in bright yellows, oranges, and reds, formed by sulfur compounds deposited during eruptions. These gases escape into space, forming a thin atmosphere around Io. However, this atmosphere is constantly being stripped away by Jupiter's magnetic field. As sulfur and oxygen ions escape from Io, they become ionized and trapped in Jupiter's magnetosphere, forming a plasma ring that rotates with the planet. The particles released by Io's volcanoes influence the magnetic field and create electrical currents that connect the moon to Jupiter. These currents generate bright auroral spots on Jupiter's poles. The interaction between the two is so strong that it can even create detectable radio emissions, which have been observed from Earth. Scientists believe that the moon's interior is highly differentiated, with a partially molten mantle and a solid core. The extreme tidal heating ensures that this internal structure remains dynamic, with magma constantly being generated and transported to the surface. This makes Io invaluable for studying volcanic processes and the effects of tidal forces on planetary bodies. The combination of intense radiation from Jupiter and the hazardous surface conditions makes it one of the most challenging destinations in the solar system. Any mission to Io would need to be heavily shielded and carefully planned to avoid the worst of these extreme environments. Despite these challenges, Io remains an intriguing target for study, offering insights into the powerful forces that shape not only the moon, but also the broader Jovian system. Each eruption and lava flow is a reminder of the immense power at work beneath Io's surface. Through Io, scientists can glimpse the raw energy of tidal forces and their ability to transform a world, making it one of the most fascinating and active moons in our celestial neighborhood. Ganymede, the largest moon and its surprising magnetic field. Ganymede is a world of superlatives, holding the title of the largest moon in the solar system. Bigger than Mercury and almost as large as Mars, It is a celestial body that could be considered a planet in its own right if it orbited the Sun instead of Jupiter. Despite its size, what truly sets Ganymede apart is its magnetic field, a feature no other moon is known to possess. The magnetic field of Ganymede was first detected by the Galileo spacecraft in the 1990s. This discovery came as a surprise, as magnetic fields are typically associated with planets, not moons. Ganymede's field is relatively weak compared to Earth's, but is still strong enough to create its own magnetosphere. This magnetosphere interacts with Jupiter's larger magnetic field, creating a complex interplay of charged particles and electromagnetic forces. The source of Ganymede's magnetic field lies deep within its interior. Scientists believe it is generated by a liquid iron or iron sulfide core, much like Earth's magnetic field is produced by its molten outer core. This requires a certain amount of internal heat to keep the core in a liquid state. While Ganymede is far from the Sun and receives little external heat, the gravitational interactions with Jupiter and neighboring moons generate tidal forces that could contribute to heating its interior. This tidal heating, though less intense than on Io, may play a critical role in maintaining the moon's magnetic dynamo. Ganymede's surface, a mix of bright icy regions and darker, older terrain, offers clues about its geological history. The bright regions are crisscrossed by grooves and ridges, indicating tectonic activity in the past. This activity may have been driven by internal heat, causing the icy crust to shift and crack. Beneath this icy surface lies a world that remains hidden, but is increasingly believed to hold an ocean of liquid water. Evidence for this subsurface ocean comes from several sources. The Galileo spacecraft detected variations in Ganymede's magnetic field that could be explained by the presence of a conductive layer beneath the surface. Salt water, with its ability to carry electric currents, is a strong candidate for this layer. Additionally, models of Ganymede's interior suggest that the immense pressure from its thick ice shell and rocky mantle could create conditions suitable for liquid water to exist. If Ganymede does indeed have an ocean, it could be one of the largest in the solar system, possibly containing more water than all of Earth's oceans combined. This ocean would be buried under a crust of ice tens to hundreds of kilometers thick, making direct exploration a significant challenge. However, the presence of such an ocean raises intriguing questions about the moon's potential for hosting life. On Earth, liquid water is a key ingredient for life, and similar environments on Ganymede could offer the necessary conditions for microbial life to exist. The interaction between Ganymede's magnetic field and Jupiter's magnetosphere creates a dynamic environment that extends beyond the moon itself. Charged particles from Jupiter's radiation belts bombard Ganymede's surface, creating auroras near its poles. These auroras, visible as faint glowing bands, are another indicator of the moon's magnetic field. Observing these auroras has provided additional evidence for the presence of a subsurface ocean, as the water layer would affect the movement of charged particles and influence the auroral patterns. Ganymede's unique combination of features, its size, magnetic field, and potential ocean, makes it a fascinating target for future exploration. Missions like JUICE are designed to study Ganymede in detail, along with its neighboring moons, Europa and Callisto. JUICE will use advanced instruments to map Ganymede's surface, probe its magnetic field, and search for signs of its hidden ocean. These observations could reveal much about the moon's history, its internal structure, and its potential for life. Callisto, the ancient moon on the edge of Jupiter's reach. Callisto, the second largest moon of Jupiter and the third largest moon in the solar system, stands apart from its Jovian siblings in many ways. Orbiting farther from Jupiter than the other major moons, Callisto is a world of contrasts, a silent, ancient sphere that has preserved the scars of billions of years. Its surface, heavily cratered and geologically inactive, offers a unique window into the history of the solar system. Callisto is one of the most heavily cratered bodies in the solar system, a clear indication that it has been geologically dormant for nearly all of its existence. Unlike other moons that have experienced volcanic activity, tectonic shifts, or resurfacing due to internal heat, Callisto has remained unchanged for billions of years. This makes it a natural time capsule, preserving a record of impacts from asteroids and comets dating back to the solar system's formation. Callisto's surface is composed primarily of ice and rock, with its crust thought to be a mixture of water ice, silicate materials, and possibly organic compounds. The craters that pockmark its surface are varied in size, from small pits to enormous basins like Valhalla and Asgard. These massive impact sites, with their central regions surrounded by concentric rings, reveal the immense forces that have shaped Callisto's face. Unlike younger surfaces on other moons, which erase such features over time, Callisto's crust has remained static, allowing these ancient scars to endure. Beneath its battered surface, Callisto is thought to have a relatively simple internal structure. Models suggest it is not fully differentiated like many other moons, meaning its layers of ice, rock, and possibly metal are not neatly separated into distinct strata. Instead, the interior appears to be a more uniform mixture, with only a gradual increase in density toward the center. This lack of differentiation suggests that Callisto never experienced the intense heat that would have been required to melt and separate its materials. Despite its apparent simplicity, Callisto may harbor a surprising feature beneath its surface. Data from the Galileo spacecraft hinted at the possibility of a subsurface ocean, similar to those suspected on Europa and Ganymede. This ocean, if it exists, would lie buried under an ice layer over 100 kilometers thick. The evidence for such an ocean comes from the Moon's interaction with Jupiter's magnetic field. If Callisto does have an ocean, it would likely be one of the most isolated in the solar system. The thick ice shell above it would insulate the ocean from the surface, preventing any exchange of material or energy. This isolation makes it less likely to support life compared to Europa or Ganymede, where surface activity might allow nutrients to reach a subsurface ocean. Still, the mere presence of liquid water on a moon so far from the Sun is a reminder of the diversity of environments in the solar system. Unlike Io, Europa, and Ganymede, which are locked in a gravitational resonance that generates tidal heating, Callisto's orbit is far enough out to avoid such interactions. As a result, it experiences very little internal heating. This lack of tidal heating is a key reason for Callisto's geological inactivity and its preservation as a frozen relic of the past. Because it lies on the edge of Jupiter's magnetosphere, Callisto also experiences significantly lower levels of radiation compared to its inner neighbors. This makes it one of the safest places in the Jovian system for future exploration. Any missions to study Callisto in detail would face fewer challenges from radiation, allowing for longer operations and potentially more ambitious investigations. Callisto's ancient surface preserves a record of the heavy bombardment period, a time when the young solar system was filled with debris left over from planet formation. By studying Callisto's craters and surface composition, scientists can gain insights into the types of objects that impacted the moons and planets during this chaotic era. Comparing Callisto to Io, Europa, and Ganymede helps scientists understand how different processes, such as tidal heating and orbital resonance, shape the evolution of moons in the same system. This comparative approach reveals the diversity of worlds that can exist around a single planet, and offers clues about the conditions that might exist on exoplanets and their moons in distant star systems. The Trojans and irregular satellites, Jupiter's hidden companions. Jupiter's influence shapes not only its moons, but also a host of smaller bodies that share its orbital space or orbit it at great distances. Among these are the Trojan asteroids and the irregular moons, a collection of celestial companions that often go unnoticed in the shadow of Jupiter's more prominent features. These objects are less studied than the Galilean moons, but are no less fascinating. providing critical insights into the history and dynamics of the solar system. The Trojan asteroids are a group of rocky bodies that orbit the Sun at roughly the same distance as Jupiter. They are clustered in two distinct regions, known as Lagrange points, one leading Jupiter in its orbit and the other trailing behind. These points represent areas of gravitational stability where the combined forces of Jupiter and the Sun create regions where objects can remain for billions of years. The Trojans are unique in that they are not bound directly to Jupiter, but share its orbital path, locked in a gravitational dance with the giant planet. There are thousands of known Trojans, and scientists believe there could be as many as 1 million larger than 1 kilometer in size. These objects vary in shape, size, and composition, hinting at a complex origin story. Some are thought to be remnants of the material that formed the outer planets, while others may have been captured from different regions of the solar system during the early chaotic period of planetary migration. These asteroids are thought to have been largely unchanged since their formation, preserving the conditions that existed when the planets were still forming. By examining their composition and distribution, scientists hope to uncover clues about how the outer planets interacted with the smaller bodies around them, and how this interaction influenced the final arrangement of the solar system. In addition to the Trojans, Jupiter is also accompanied by a large and varied collection of irregular moons. These moons are distinct from the Galilean moons and other regular satellites, which have nearly circular orbits that align with Jupiter's equatorial plane. Irregular moons, by contrast, follow highly elliptical and often inclined orbits, and many move in a retrograde direction, meaning they orbit Jupiter in the opposite direction of its rotation. The irregular moons are thought to have been captured by Jupiter's gravity rather than forming alongside the planet. Their irregular orbits and diverse characteristics suggest they may have originated as asteroids or comets from the Kuiper Belt or beyond. Once captured, their paths were likely shaped by interactions with other moons and the planet's gravity, leading to the complex and chaotic orbits observed today. Some are small, less than 1 kilometer across, while others, like Himalaya, are significantly larger, with diameters of over 150 kilometers. These moons often form families, groups of objects that share similar orbital characteristics and are thought to have originated from a common parent body. Collisions between captured objects likely created these families, scattering debris into distinct orbits around Jupiter. The study of irregular moons provides valuable insights into the processes of capture and collision in the early solar system. By analyzing their orbits and compositions, scientists can piece together the history of Jupiter's interactions with other celestial bodies. These moons also help in understanding the dynamics of irregular orbits, which can have implications for the study of objects in other planetary systems. Jupiter's influence on its Trojans and irregular moons extends beyond their orbits. The planet's immense gravity shapes their surfaces and interactions, and its radiation environment can alter their chemical compositions over time. For the irregular moons, this radiation can cause surface materials to darken and redden, a process observed on many of these distant satellites. NASA's upcoming Lucy mission is specifically designed to visit several Trojan asteroids, marking the first time these objects will be studied up close. By examining their surface features, compositions, and orbits, Lucy aims to provide a deeper understanding of their origins and their role in the broader context of the solar system. Meanwhile, advancements in telescopes and observation techniques continue to reveal new irregular moons around Jupiter. These discoveries expand our understanding of the diversity and complexity of the planet's satellite system, highlighting the intricate gravitational web that binds these objects to Jupiter. Each new finding helps scientists reconstruct the history of Jupiter's formation and its long-lasting influence on its surroundings. Cosmic Shield: How Jupiter Guards the Inner Solar System. Jupiter's immense size and gravitational pull make it one of the most influential bodies in shaping the environment of the inner solar system. Acting as a cosmic shield, the gas giant protects Earth and its neighboring planets by diverting, capturing, or ejecting countless comets and asteroids that might otherwise pose a significant threat. This role, often described as that of a cosmic vacuum cleaner, is massively important for the stability and habitability of the inner solar system. As the largest planet in the solar system, Jupiter exerts a gravitational pull that far exceeds that of any other planet. This influence extends across vast distances, drawing in objects from the outer reaches of the solar system and altering their trajectories. Many comets and asteroids that approach the inner solar system are redirected by Jupiter's gravity, often into safer orbits or entirely out of the solar system. Without Jupiter's presence, these objects would have a much greater chance of colliding with Earth or other inner planets. Evidence of Jupiter's protective role can be found in the orbits of short-period comets. These comets, which take less than 200 years to complete an orbit around the Sun, often originate in the Kuiper Belt, a region of icy bodies beyond Neptune. As they move inward, their paths are frequently influenced by Jupiter's gravity. Some are pulled into stable orbits that keep them from venturing too close to Earth, while others are flung back out into the outer solar system. In some cases, Jupiter's gravitational pull causes these comets to collide with the planet itself, effectively removing them as potential threats to the inner planets. One of the most dramatic demonstrations of Jupiter's role as a cosmic shield occurred in 1994 when comet Shoemaker Levy 9 collided with the planet. The comet, which had been captured by Jupiter's gravity years earlier, broke apart into a series of fragments that struck the planet's atmosphere over several days. The impacts created massive scars in Jupiter's clouds, visible from Earth, and released energy equivalent to millions of nuclear bombs. While the collision was catastrophic for the comet, it was a showcase of Jupiter's ability to absorb or intercept objects that might otherwise have continued on a path toward the inner solar system. The planet also plays a crucial role in shaping the asteroid belt, a region of rocky debris located between Mars and Jupiter. The asteroid belt contains millions of objects, ranging from small pebbles to massive bodies hundreds of kilometers across. Jupiter's gravity helps to maintain the belt's structure, preventing its material from coalescing into a planet. At the same time, it can eject asteroids from the belt or send them into new orbits, some of which bring them closer to Earth. The interaction between Jupiter and the asteroid belt has both protective and hazardous effects. On one hand, Jupiter's gravity prevents many asteroids from reaching the inner solar system, acting as a barrier that limits the number of potential impactors. On the other hand, gravitational interactions, known as resonances, can destabilize the orbits of some asteroids, sending them on trajectories that cross Earth's path. Jupiter plays a key role in the overall dynamics of the solar system. Its gravitational presence helps to stabilize the orbits of the inner planets, reducing the likelihood of major disruptions over long timescales. Without Jupiter, the inner solar system might experience more frequent close encounters with comets and asteroids, increasing the risk of catastrophic impacts. This stability has likely been a critical factor in the development and persistence of life on Earth. Jupiter's protective role extends to the realm of long-period comets, which originate in the distant Oort cloud, a vast reservoir of icy bodies at the edge of the solar system. These comets, with orbital periods of thousands or even millions of years, are often perturbed by gravitational interactions with passing stars or the galactic tide. As they journey inward, they encounter Jupiter's gravitational field, which can dramatically alter their paths. In many cases, Jupiter redirects these comets away from the inner solar system, reducing the likelihood of an impact with Earth. Despite its protective role, it is not an infallible shield. The planet's gravity can also act as a slingshot, accelerating objects towards the inner solar system. This dual effect means that while Jupiter reduces the overall number of potential impactors, it also increases the velocity and energy of some objects that do reach Earth. These high-speed impacts can be particularly destructive. Astronomers use computer models to study how the planet's gravity influences the trajectories of comets and asteroids over time. These models reveal the intricate dance of objects within the solar system, showing how Jupiter's presence shapes their fates. Observations of impact scars on Jupiter's surface, as well as data from spacecraft, provide further insights into the planet's interactions with small bodies. In other planetary systems, the presence of a massive planet like Jupiter could play a similar role, shielding potentially habitable worlds from frequent impacts. Studying the dynamics of these systems can help scientists identify exoplanets that might have stable environments conducive to life. How Jupiter's gravity shapes the solar system's architecture. Jupiter's immense mass, more than twice that of all the other planets combined, gives it the ability to shape and influence the movements of countless objects, from the smallest asteroids to entire planets. Over billions of years, this gravitational force has played a central role in sculpting the architecture of the solar system as we know it today. As the Sun formed and its surrounding disk of gas and dust started to coalesce into planets, Jupiter's mass and position exerted a strong influence on the distribution of material. It acted as a barrier, preventing the flow of material from the outer regions into the inner solar system. This is one reason why the inner planets, including Earth, are smaller and made mostly of rock and metal, while the outer planets are larger and rich in gas and ice. Jupiter's gravitational pull essentially swept up much of the lighter material, leaving the inner regions depleted. Jupiter's gravity also helped to shape the asteroid belt. This region is filled with rocky and metallic objects that never managed to form a planet. One of the key reasons for this is Jupiter's influence. Its gravitational pull creates areas of instability within the asteroid belt, known as Kirkwood gaps. These gaps are regions where the orbital periods of asteroids would be in resonance with Jupiter, meaning their orbits would align with Jupiter's in a way that leads to repeated gravitational nudges. Over time, these nudges destabilize the asteroids' orbits, causing them to be ejected from the belt or sent on collision courses with other objects. Beyond the asteroid belt, Jupiter's gravity has also shaped the orbits of the other planets. During the early stages of the solar system's formation, gravitational interactions between Jupiter and other large bodies likely caused significant shifts in their orbits. Some scientists believe that Jupiter may have migrated inward toward the Sun before reversing course and moving back out to its current position. This migration could have disrupted the orbits of other planets and smaller objects, reshaping the solar system's layout. In particular, this process might explain the presence of the asteroid belt and the distribution of planets in the inner and outer regions. Jupiter's gravity has also affected the Kuiper belt. By interacting with Neptune, Jupiter indirectly helps to control the movements of objects in this distant region. Some of these interactions result in Kuiper belt objects being sent into the inner solar system, where they become comets. Many of these comets are eventually captured by Jupiter's gravity, either being ejected from the solar system entirely or pulled into orbits that keep them away from the inner planets. The Trojans are another example of the planet's gravitational influence. These asteroids are located in two clusters, one ahead of Jupiter and one behind it. They are thought to be remnants of the early solar system, preserved by Jupiter's gravity in these unique locations. Jupiter's gravitational reach is so extensive that it even influences the orbits of comets that originate in the Oort cloud. As these comets are perturbed by passing stars or the galactic tide, they are drawn inward toward the Sun. Many of them pass close to Jupiter, where its gravity alters their paths. Some are captured and become short-period comets, while others are ejected entirely from the solar system. In this way, Jupiter controls the flow of material from the outermost regions of the solar system. The planet's gravity also has a more subtle but equally important effect on the stability of the entire solar system. By anchoring the outer planets and influencing their orbits, Jupiter helps to maintain the overall balance of the system. Without Jupiter's presence, the orbits of the inner planets might be more chaotic, with frequent close encounters leading to destabilization. Even today, Jupiter regularly interacts with passing asteroids and comets, altering their orbits and sometimes capturing them as temporary moons. These interactions can also result in collisions with Jupiter itself. The scars left by these impacts are a vivid reminder of Jupiter's role within the solar system. The dance of resonance, Jupiter's gravitational influence on its moons. Jupiter's moons are a dynamic family of celestial objects, each unique in its composition and behavior. Among the most fascinating aspects of this system is the intricate dance of resonance that occurs between its largest moons. These orbital resonances are a direct result of Jupiter's immense gravitational pull and the gravitational interactions between the moons themselves. Together, they create a rhythmic and interconnected system that shapes the moon's orbits, geological activity, and overall evolution. The four largest moons of Jupiter are collectively known as the Galilean moons, named after Galileo Galilei, who first observed them in 1610. Three of these moons, Io, Europa, and Ganymede, are locked in a gravitational relationship called a Laplace resonance. This resonance means that their orbital periods are connected in a precise ratio. For every 4 orbits that Io completes around Jupiter, Europa completes exactly 2, and Ganymede completes 1. This synchrony is not a coincidence, but rather the result of billions of years of gravitational interactions. Resonance plays a crucial role in maintaining the stability of the moon's orbits. Without it, the gravitational forces between the moons could destabilize their paths over time, leading to chaotic motion or even collisions. Instead, the resonance acts as a stabilizing mechanism, ensuring that the moons remain in predictable orbits. This relationship does more than just keep the moons in line. It also has profound effects on their internal dynamics and surface features. As Io, Europa, and Ganymede move in and out of each other's gravitational fields, their orbits are slightly elongated. This elongation causes the moons to flex as they orbit Jupiter. The constant stretching and squeezing generate friction within their interiors, which is then converted into heat. For Io, this tidal heating is extreme. Its surface is covered with erupting volcanoes, all fueled by the heat generated through its interaction with Jupiter and the other moons. Europa also experiences tidal heating, though to a lesser extent than Io. This heating is thought to keep an ocean of liquid water beneath Europa's icy crust from freezing solid. The presence of this subsurface ocean has made Europa a prime candidate in the search for extraterrestrial life. The same gravitational forces that create the resonance may also drive hydrothermal activity on the ocean floor, providing the kind of energy-rich environment that could support microbial life. Ganymede, the largest moon, experiences less tidal heating than Io or Europa, but its inclusion in the resonance still influences its interior. Ganymede is unique among the moons in having its own magnetic field, which suggests the presence of a liquid metallic core. The resonance likely contributes to the internal energy balance that sustains this molten core. Callisto, the outermost Galilean moon, does not participate in the Laplace resonance. As a result, it experiences far less tidal heating and has remained geologically inactive for billions of years. Its surface is heavily cratered, a testament to its ancient and undisturbed history. Despite its isolation from the resonance, Callisto's orbit is still influenced by Jupiter's gravity, and its presence adds to the overall dynamics of the Jovian moon system. The Laplace resonance among Io, Europa, and Ganymede is not static. Over time, the interactions between the moons and Jupiter's gravitational field cause gradual changes in their orbits. For instance, as the moons exchange angular momentum, their distances from Jupiter can shift slightly. These changes occur on timescales of millions to billions of years, making the resonance a dynamic and evolving system. Scientists continue to study the Laplace resonance and the broader Jovian system using both ground-based telescopes and space missions. The Galileo spacecraft, which orbited Jupiter from 1995 to 2003, provided invaluable data on the moons and their interactions. More recently, the Juno mission has focused on Jupiter itself, but has also offered insights into the behavior of its moons. Future missions aim to explore the moons in greater detail, particularly Europa and Ganymede. These missions will investigate not only the moon's surfaces and interiors, but also the mechanisms of resonance that connect them. By understanding how the moons influence each other and their host planet, scientists hope to gain deeper insights into the processes that shape planetary systems. Many of the exoplanets discovered to date are part of multi-planet systems, where gravitational interactions play a significant role in their evolution. The lessons learned from Jupiter and its moons can help scientists interpret the dynamics of these distant worlds. Jupiter's faint rings. Why they're so different from Saturn's. Jupiter's rings are an understated feature of the giant planet, often overshadowed by the dramatic and iconic rings of Saturn. Unlike the bright, expansive, and easily visible rings of its neighbor, Jupiter's rings are faint, delicate, and composed of different materials that make them far less noticeable. These rings weren't even discovered until the Voyager missions in the late 1970s, a testament to their subtlety and the difficulty in observing them from Earth. Jupiter's rings are made up of three main components: the halo ring, the main ring, and the gossamer rings. Each has its own distinct characteristics and composition, but all share a common trait. They are primarily composed of fine dust particles rather than the icy chunks that dominate Saturn's rings. This fundamental difference is the key to understanding why Jupiter's rings are so faint and challenging to observe. The innermost part of Jupiter's ring system is the halo ring, a thick toroidal region of fine particles that sits closest to the planet. It is not a well-defined ring like those seen around Saturn, but rather a diffuse cloud of dust that extends both above and below Jupiter's equatorial plane. The particles in the halo ring are thought to be incredibly small, likely less than a micron in diameter. These tiny grains scatter light poorly, making the halo ring nearly invisible, except when observed in specific wavelengths of light. Beyond the halo ring lies the main ring, which is more sharply defined but still faint compared to the rings of other planets. The main ring is relatively narrow, stretching only a few thousand kilometers in width, but it is much thinner in vertical extent. This ring is composed of slightly larger dust particles, though they are still far smaller than the icy chunks found in Saturn's rings. The main ring owes its existence to the small inner moons of Jupiter, such as Metis, Adrastea, Amalthea, and Thebe. These moons act as both sources and sculptors of the ring material. The primary source of dust for the main ring is the continual bombardment of these small moons by micrometeoroids. When these tiny meteoroids collide with the surfaces of the moons, they create high-speed impacts that eject dust and debris into space. Because the moons are relatively small and have weak gravitational fields, much of this material escapes their surfaces and becomes trapped in orbit around Jupiter. Over time, this process replenishes the main ring with fresh material, maintaining its existence despite the natural tendency for dust to spiral inward toward the planet. Farther out from the main ring are the gossamer rings, a pair of extremely faint and diffuse rings named after their ethereal appearance. These rings are associated with the moons Amalthea and Thebe, which contribute dust in a manner similar to the inner moons. The gossamer rings extend much farther from Jupiter than the main ring and are so faint that they can only be detected using highly sensitive instruments. Their composition is similar to that of the main ring, consisting of tiny dust particles that scatter light weakly. One of the reasons Jupiter's rings are so different from Saturn's is the environment in which they exist. Jupiter's strong gravitational field and intense radiation environment play a significant role in shaping the rings. The planet's powerful magnetosphere interacts with the charged particles in the rings, influencing their distribution and dynamics. Unlike Saturn, which has a more benign radiation environment, Jupiter's harsh conditions make it difficult for larger particles or icy chunks to persist in its rings. Any such material is quickly broken down or eroded by radiation and micrometeoroid impacts. The composition of Jupiter's rings also reflects the nature of the moons that supply the material. Saturn's rings are primarily made of water ice, giving them their bright and reflective appearance. In contrast, the dust particles in Jupiter's rings are thought to contain silicates and other non-icy materials, which are much darker and less reflective. Jupiter's strong gravitational pull causes a phenomenon known as Poynting-Robertson drag, where the particles slowly spiral inward toward the planet. Additionally, the charged particles in the rings are influenced by Jupiter's magnetic field, which can accelerate their loss by ejecting them from the system or causing them to collide with the planet's atmosphere. These processes ensure that the rings are constantly losing material, which must be replenished by the moons to maintain their presence. Despite their faintness, Jupiter's rings are scientifically significant because they are a dynamic system, constantly changing as new material is added and old material is lost. They serve as a natural laboratory for studying the behavior of dust and small particles in space, offering insights that can be applied to other ring systems and dust environments in the solar system and beyond. Observing Jupiter's rings requires advanced instruments and specific conditions. The Voyager spacecraft were the first to capture images of the rings, revealing their existence and basic structure. Ground-based telescopes have also contributed to our understanding, though their capabilities are limited by the faintness of the rings and the glare of Jupiter itself. How Jupiter's moons feed and shape its ring system. Jupiter's ring system, faint and elusive as it is, owes its existence to the dynamic interaction between the planet and its moons. Without them, the rings would not only look different, but might not exist at all. The inner moons orbit close to Jupiter, within the region where the rings are found. Their surfaces are constantly bombarded by tiny meteoroids, which generate enough energy to blast small particles of material off the surface. This process, known as micrometeoroid impact erosion, is a steady source of dust that feeds the rings. Jupiter's immense gravity ensures that much of that material remains in orbit around the planet, where it gradually spreads out to form the rings. The particles in the rings are often less than a micron in size. These tiny grains are light enough to be influenced by forces other than gravity, such as radiation pressure from the Sun and electromagnetic forces within Jupiter's powerful magnetosphere. Each moon contributes to specific parts of the ring system. The main ring, which is the brightest and most defined of Jupiter's rings, is closely associated with Metis and Adrastea. These two moons are embedded within the ring itself, and their surfaces are continuously supplying material. The Gossamer rings, which are much fainter and more diffuse, are linked to Amalthea and Thebe. These moons orbit farther from Jupiter, and their contributions create rings that extend over a much larger area. The gravitational influence of the moons creates subtle patterns within the rings, such as waves or gaps. For example, as Metis and Adrastea orbit within the main ring, their gravitational pull helps to define the ring's edges and thickness. These moons essentially act as shepherds, maintaining the ring's shape and preventing it from spreading out too much. Jupiter's magnetosphere also plays a significant role in the behavior of the ring particles. The dust in the rings becomes electrically charged due to interactions with the magnetosphere. Once charged, these particles are influenced by the magnetic field, which can alter their orbits or even eject them from the ring system entirely. This interaction adds another layer of complexity to the relationship between the moons and the rings, as the materials supplied by the moons must constantly contend with the forces of Jupiter's magnetic environment. The dust particles don't stay in the rings indefinitely. Over time, the particles spiral inward toward Jupiter thanks to Poynting-Robertson drag. This effect occurs when sunlight exerts a tiny force on the dust particles, causing them to lose angular momentum and gradually move closer to the planet. As the particles drift inward, they eventually burn up in Jupiter's atmosphere. This constant loss of material means that the rings are in a state of continual renewal. Some of the dust ejected from one moon could theoretically end up on another moon or even contribute to the ring system. This exchange is facilitated by the complex gravitational and electromagnetic forces within Jupiter's system, creating a web of interactions that links the moons and the rings in ways that scientists are still working to fully understand. The Voyager spacecraft were the first to reveal the existence of the rings. Later missions have allowed scientists to map the rings, analyze their composition, and study the interactions between the rings and the moons. Despite these advances, many questions remain unanswered, such as the precise rates at which the moons supply material to the rings and the detailed mechanisms by which the dust is distributed. Could there be life in Jupiter's clouds? Jupiter appears inhospitable at a glance. Its surface is a seething mass of gases. Its atmosphere is filled with radiation, and the pressures in its lower layers would crush anything Earth-like. However, scientists have long been intrigued by the upper cloud layers of Jupiter, where conditions might be more forgiving. In these upper reaches, far from the crushing depths below, some have speculated that the right combination of factors could allow for the existence of microbial life. The clouds of Jupiter are a swirling mixture of hydrogen, helium, ammonia, methane, and most importantly, water vapor. Water is a key ingredient when it comes to searching for life, and in Jupiter's atmosphere, there are traces of it. Though not as abundant as on Earth, water exists in the form of tiny droplets within the cloud layers. These droplets, suspended high above the planet's surface, could theoretically provide a medium where life might find a foothold. On Earth, microbial life thrives in water-rich environments, even under extreme conditions, such as high acidity or low temperatures. One of the most compelling arguments for the potential of life in Jupiter's clouds comes from the temperature range found in certain layers. While the deeper parts of Jupiter's atmosphere are unbearably hot, due to the intense pressure, the upper layers are much cooler. In some regions, the temperatures range between -40 degrees Celsius and 30 degrees Celsius, which is comparable to environments where extremophiles, or life forms adapted to extreme conditions, have been found on Earth. These temperatures might allow for the existence of liquid water droplets, which could act as tiny habitats for microorganisms. The challenge, however, lies in the chemical makeup of Jupiter's clouds. Ammonia, a dominant component, creates a highly alkaline environment. On Earth, most life forms struggle to survive in conditions that are too alkaline. Yet some extremophiles have adapted to live in highly basic environments, such as soda lakes or alkaline hydrothermal vents. If life were to exist in Jupiter's clouds, it would likely need similar adaptations, thriving in a chemistry vastly different from what we are accustomed to. Another factor is the energy sources available in Jupiter's atmosphere. Lightning is a common phenomenon in Jupiter's clouds, producing bursts of energy that could drive chemical reactions. On Earth, lightning is thought to have played a role in the formation of complex organic molecules, which are the building blocks of life. If similar processes occur on Jupiter, the lightning could potentially spark the creation of molecules like amino acids or even more complex compounds. These molecules, suspended in the water droplets, could provide the foundation for microbial life. Jupiter's immense magnetic field also contributes to the energy dynamics in its atmosphere. The interaction between the magnetic field and charged particles creates auroras and generates radiation belts around the planet. While this radiation is intense and deadly closer to the surface, in the upper atmosphere, it could act as a catalyst for certain chemical reactions. These reactions might help create or sustain molecules that are essential for life. However, the radiation also poses a threat, as it could break down these molecules, before they have a chance to accumulate or form more complex structures. High in Earth's atmosphere, microbes have been found drifting in the clouds. These airborne life forms are incredibly resilient, surviving on minimal nutrients and enduring ultraviolet radiation from the sun. If life on Earth can adapt to such conditions, it raises the question of whether similar adaptations could occur elsewhere, even on a planet as different as Jupiter. It is fascinating to think about the potential life cycle of any hypothetical organisms in Jupiter's atmosphere. The cloud layers are not static. They are constantly in motion due to the planet's powerful winds and turbulence. Microbial life would need to remain within a specific altitude range where conditions are most favorable. This could mean that such organisms are buoyant, floating on air currents and staying within the temperate zone. If they were to drift too high, they would be exposed to extreme cold and ultraviolet radiation. If they fell too low, they would encounter crushing pressures and high temperatures. When Galileo's probe descended into the clouds, it detected a variety of chemical compounds and measured the temperature and pressure at different altitudes. The data revealed a complex and dynamic atmosphere, with conditions that are not entirely incompatible with the idea of life. Future missions, equipped with more advanced instruments, could provide a clearer picture of whether life is even remotely possible in this environment. NASA's proposed Dragonfly mission, which aims to study Titan, showcases the type of technology that could one day be adapted for exploring Jupiter's atmosphere. Probes capable of sampling the cloud layers and analyzing their composition in detail would be crucial for determining whether the conditions are suitable for life. If life can exist in such an extreme and alien environment, it would expand our understanding of biology and the potential for life elsewhere in the universe. It would suggest that life is not confined to Earth-like planets, but could emerge in places we once considered impossible. Jupiter's clouds, with their unique combination of challenges and possibilities, remain a tantalizing target for this exploration. What happens if Jupiter's core collapses? Jupiter's core is thought to be a dense region of heavy elements, possibly surrounded by a layer of metallic hydrogen and enveloped by the planet's thick atmosphere of hydrogen and helium. This core is not solid like Earth's, but is theorized to be a mixture of rock, ice, and metals under immense pressure and extreme temperatures. The existence and precise state of Jupiter's core remain subjects of ongoing study, but it plays a critical role in the planet's overall structure and stability. If this core were to destabilize or collapse, the effects would likely ripple across the solar system. One of the most immediate consequences of a core collapse would be a dramatic redistribution of mass within Jupiter. The planet's immense gravity, which holds its atmosphere and surrounding moons in place, depends on the stability of the core and the layers above it. A collapse could lead to violent internal shifts, releasing energy and potentially triggering massive atmospheric disturbances. Jupiter's iconic bands of clouds and storms, including the Great Red Spot, could be thrown into chaos, creating turbulence on a scale never before seen. The planet's powerful jet streams might change direction or dissipate entirely, altering the weather patterns that have persisted for centuries. Jupiter's magnetic field could undergo significant changes. If the core's collapse disrupts the flow of charged particles within the planet, the magnetic field might weaken or fluctuate unpredictably. These changes could have a profound impact on Jupiter's surrounding environment, including its interaction with the solar wind and the charged particles in its magnetosphere. If the field were to weaken or fluctuate, it could disrupt the delicate balance that has shaped the environments of the Jovian moons. A change in the magnetic field could, for example, potentially quieten Io's eruptions or trigger new patterns of volcanism. The Galilean moons are inextricably linked to Jupiter's gravitational fields. A core collapse could disrupt the orbital resonances among these moons, causing them to drift into new positions or even risk collisions. Beyond the immediate vicinity of Jupiter, a core collapse could have effects that reach the inner solar system. If the core's collapse disrupted Jupiter's gravitational stability, it could change the trajectories of various objects, increasing the likelihood of collisions with Earth or other planets. Jupiter's gravity has a significant influence on the asteroid belt's structure, creating Kirkwood gaps through orbital resonances. Any destabilization to those resonances could send asteroids on new, unpredictable paths. This could lead to an increase in asteroid impacts on Earth, potentially creating extinction-level events. Jupiter's role as a gravitational anchor helps to maintain the current configuration of planetary orbits. Any significant disruption to its mass distribution or gravitational pull could introduce perturbations to the orbits of other planets, potentially creating long-term instabilities. The energy released by a collapsing core could also manifest as a burst of radiation or heat. Depending on the scale of the event, this energy could have observable effects from Earth. Telescopes might detect changes in Jupiter's brightness or even outbursts of material from the planet's atmosphere. The search for analogues. Is Jupiter a failed star? Jupiter's massive presence in the solar system, its composition dominated by hydrogen and helium, and its internal heat all raise an intriguing question. Could Jupiter be considered a failed star? To explore this, it's important to compare Jupiter's characteristics to those of brown dwarfs and protostars, which occupy a sort of middle ground between planets and stars. Stars, including our Sun, are powered by nuclear fusion. At their cores, immense gravitational pressure forces hydrogen atoms to fuse into helium, releasing vast amounts of energy. For this process to occur, a celestial object must have a certain critical mass. For hydrogen fusion to ignite, that mass is approximately 75 times the mass of Jupiter. This stark difference immediately sets Jupiter apart from stars. It simply isn't massive enough to achieve the core pressures and temperatures needed for fusion. However, there exists a class of objects known as brown dwarfs that blur the line between planets and stars. Brown dwarfs are often referred to as failed stars because they form like stars, collapsing under gravity from a cloud of gas and dust, but they never gather enough mass to sustain hydrogen fusion. They typically have masses between about 13 and 75 times that of Jupiter. Despite their inability to sustain fusion, brown dwarfs can fuse a heavier isotope of hydrogen called deuterium, but even this process is short-lived compared to the life of a true star. Jupiter's mass, while impressive, is only about 1/80th of the mass required for hydrogen fusion, and falls well below the threshold for deuterium fusion as well. This means that, by the most fundamental definition, Jupiter does not qualify as a brown dwarf. However, its composition and internal dynamics do share some intriguing similarities with these failed stars. Jupiter, like brown dwarfs and stars, is primarily composed of hydrogen and helium. In fact, the ratios of these elements in Jupiter's atmosphere closely resemble the primordial mix of gases that formed in the early solar system. This suggests that Jupiter, much like stars and brown dwarfs, formed from the same building blocks. It is believed that Jupiter formed through a process known as core accretion, where a solid core grew by accumulating gas and dust, eventually pulling in a thick atmosphere of hydrogen and helium. This differs from the process that forms stars and brown dwarfs, which condense directly from large clouds of gas, but the end result, a hydrogen-dominated body, is strikingly similar. While stars generate heat through nuclear fusion, Jupiter's heat comes from the slow contraction of its mass under gravity, a process known as Kelvin-Helmholtz contraction. As the planet slowly shrinks, gravitational potential energy is converted into heat, which escapes into space. This phenomenon also occurs in brown dwarfs, particularly during their early stages. Jupiter emits more heat than it receives from the Sun, a characteristic it shares with brown dwarfs and young stars. Jupiter's magnetic field is the strongest of any planet in the solar system. Brown dwarfs, too, are known to have powerful magnetic fields, and some even exhibit auroras similar to those seen on Jupiter. The presence of such a strong magnetic field suggests that the internal dynamics of Jupiter and brown dwarfs share some commonalities, even if the scale and processes differ. Jupiter's immense mass and gravitational influence shapes the orbits of other planets, and it acts as a gatekeeper for comets and asteroids. In this way, Jupiter plays a role similar to that of a star in a planetary system, organizing and stabilizing the smaller bodies around it. Its gravitational pull is so strong that it even captured some moons that might have formed elsewhere, adding to its resemblance to a miniature solar system. Despite these similarities, there are clear and fundamental differences that keep Jupiter firmly in the category of planets. The lack of nuclear fusion is the most obvious, but other distinctions lie in its formation and structure. Stars and brown dwarfs are born from the gravitational collapse of gas clouds, a process that leads to higher temperatures and pressures at their cores. Jupiter, on the other hand, formed in the protoplanetary disk of our young Sun, accumulating material that never reached the critical mass needed to trigger fusion. Astronomers have identified planets around other stars that are larger than Jupiter, but still lack the characteristics of brown dwarfs. These findings show that there is a wide spectrum of planetary and substellar objects, with Jupiter sitting at the upper end of the planetary range rather than crossing into the realm of failed stars. In recent years, the study of exoplanets and brown dwarfs has provided valuable context for understanding Jupiter's place in the cosmic hierarchy. Observations of massive gas giants in other systems reveal that Jupiter is not unique, but rather one example of a class of planets that form around stars. These studies also highlight the diversity of planetary systems, showing that while Jupiter shares some traits with brown dwarfs, it is ultimately shaped by its environment as a planet orbiting a star. Could Jupiter's moons become the cradles of interstellar civilization? The icy worlds around Jupiter seem inhospitable at first glance. Yet Europa, Ganymede, and Callisto offer intriguing possibilities for becoming stepping stones to the stars. Each moon presents unique features that could support human activity and serve as bases for interstellar exploration. But the challenges of radiation, cold, and resource extraction would require ingenious solutions. Europa stands out as one of the most promising candidates for colonization. Beneath its thick shell of ice lies a global ocean of liquid water, kept warm by tidal heating from its gravitational interactions with Jupiter and neighboring moons. This subsurface ocean may contain more water than all of Earth's oceans combined, making it a tantalizing target for exploration and potentially a source of life-sustaining resources. The ice crust itself, estimated to be between 10 and 30 kilometers thick, could provide a natural shield against radiation from Jupiter's powerful magnetosphere. Any human habitats on Europa would likely be built beneath this icy barrier, tapping into the subsurface ocean for water and other materials. Accessing Europa's ocean would require advanced technology, including drills or melt probes capable of penetrating the ice. Once through, the ocean could offer not only water, but also minerals and salts dissolved from the moon's rocky interior. Hydrothermal vents on the ocean floor, if they exist, might harbor life forms, or at least provide valuable energy sources. Such an environment could become a hub for scientific research, allowing humans to study an alien ocean up close while gathering resources for further exploration. Europa's biggest challenge is radiation. The Moon is bombarded by high-energy particles trapped in Jupiter's magnetic field, creating an environment hostile to life on the surface. Radiation levels are so intense that unshielded humans could only survive for a few hours. Any colony on Europa would need robust protection, such as habitats buried deep in the ice or constructed with radiation-resistant materials. Advanced technologies like electromagnetic shielding could also play a role in mitigating the radiation threat. Unlike Europa, Ganymede has its own magnetic field, the only moon in the solar system to do so. This magnetic field provides some protection from Jupiter's radiation, though it is not as effective as Earth's. Ganymede's surface is a mix of water ice and rocky material. and scientists believe it also harbors a subsurface ocean, though deeper beneath the surface than Europa's. The presence of this ocean could make Ganymede a valuable source of water and minerals. Ganymede's size is another advantage. Its surface area is larger than that of Mercury, providing ample space for building habitats and infrastructure. Its lower radiation levels compared to Europa make it a more forgiving environment for long-term human presence. However, its greater distance from Jupiter means that it experiences less tidal heating, making its subsurface ocean harder to access. Colonies on Ganymede might rely more on surface-based resources, such as ice mining and solar power, though the weak sunlight at Jupiter's distance from the Sun would necessitate highly efficient solar panels or alternative energy sources. Unlike Europa and Ganymede, Callisto is geologically inactive, with an ancient surface that has remained largely unchanged, preserving a record of the early solar system. Callisto's lack of geological activity means it has no subsurface ocean warmed by tidal forces, though there is evidence that it may still harbor a layer of liquid water deep beneath its crust. Its greatest advantage is its location. Being farther from Jupiter, it lies outside the worst of the planet's radiation belts. This makes Callisto the safest of Jupiter's large moons for human habitation. Its relatively stable environment, combined with abundant water ice, makes it an appealing option for a colony. The Moon's isolation from Jupiter's intense radiation and gravitational influence could make it a quieter, safer base for long-term human activity. Despite its geological inactivity, Callisto's surface materials could still be useful. Water ice could be melted for drinking water or split into hydrogen and oxygen for rocket fuel and breathable air. The Moon's rocky components might also contain useful minerals for building and maintaining habitats. Callisto's distance from Jupiter means that it would be less affected by the planet's gravitational tides, providing a stable platform for launching missions deeper into the solar system or even beyond. One of the most exciting possibilities for colonizing these moons is their potential role as waypoints for interstellar exploration. Situated in the outer solar system, they could serve as staging grounds for missions to other stars. Their resources, including water and minerals, could support the construction and fueling of spacecraft, while their low gravity compared to Earth's would make launching interstellar missions more energy efficient. A network of colonies on Europa, Ganymede, and Callisto could form a critical part of humanity's expansion into the cosmos. The challenges of colonizing these moons are immense, but they are not insurmountable. Advances in technology, particularly in areas like radiation shielding, energy generation, and autonomous systems, would be essential for making these environments habitable. Robotics could play a crucial role in building and maintaining infrastructure, reducing the need for humans to work in hazardous conditions. Innovations in life support systems, including closed-loop recycling of air and water, would be vital for sustaining long-term human presence. In addition to technological challenges, there are ethical considerations to address. Europa's subsurface ocean, for example, could potentially harbor microbial life. If such life exists, it would be the first discovery of extraterrestrial biology. Any human activity on Europa would need to carefully balance exploration and resource extraction with the protection of potential alien ecosystems. International agreements and planetary protection protocols would likely guide such efforts, ensuring that humanity's expansion does not come at the expense of other forms of life. Mining Jupiter: the challenges and rewards of harvesting. Metallic hydrogen. Jupiter's core, where metallic hydrogen is believed to exist, lies beneath tens of thousands of kilometers of thick atmosphere. As one descends, the pressure and temperature increase rapidly. At depths of about 20,000 kilometers, hydrogen is compressed into a metallic state. This metallic hydrogen is not like the shiny metal we are familiar with on Earth, instead being a highly dense, electrically conductive fluid. The first obstacle to mining metallic hydrogen is simply getting through Jupiter's atmosphere. The planet's gravity is enormous, more than 2.5 times that of Earth. Any spacecraft attempting to descend into Jupiter would face crushing forces and immense heat. The atmosphere's pressure increases so dramatically with depth that even the strongest materials known to humanity might not survive. To put it into perspective, the pressures at the depth where metallic hydrogen exists are millions of times greater than atmospheric pressure on Earth. This is far beyond the tolerances of current engineering. Even if a vehicle could be designed to withstand the pressures, it would need to navigate through Jupiter's violent weather systems. Winds can reach speeds of hundreds of kilometers per hour, and lightning bolts far more powerful than those on Earth are common. These conditions would make descent not only dangerous, but also unpredictable, as storms could easily damage or destroy even the most advanced equipment. Assuming it were possible to reach the depths where metallic hydrogen exists, the next challenge would be extracting it. Metallic hydrogen is not a solid that can be mined with drills or excavators. It is a fluid, meaning that any attempt to gather it would involve containment systems capable of handling its extreme density and properties. Such systems would need to prevent the material from decompressing as it is brought to the surface, as metallic hydrogen is only stable under immense pressure. If the pressure is released, it would likely revert to its gaseous form, potentially resulting in explosive reactions. The planet's strong gravity means that any spacecraft carrying metallic hydrogen would need enormous amounts of energy to escape its pull. This energy requirement would offset much of the material's potential benefits unless an efficient method of transport could be developed. One possibility is using the energy from the metallic hydrogen itself, assuming it could be stabilized and used as a high-energy fuel. Thus, to mine metallic hydrogen, one might already need metallic hydrogen-powered systems, a classic chicken and egg scenario. Despite these challenges, the potential rewards of mining metallic hydrogen are so significant that some scientists and engineers believe it is worth exploring. Metallic hydrogen's energy density could revolutionize space travel. A single kilogram of metallic hydrogen could potentially store more energy than the most advanced chemical batteries, making it an ideal fuel for interplanetary and interstellar travel. Superconducting magnets made from metallic hydrogen could be used in advanced medical imaging systems, maglev trains, and even fusion reactors. The material's unique properties could also lead to breakthroughs in computing, enabling faster and more powerful processors. Studying this exotic form of matter could deepen our understanding of Jupiter and other gas giants, as well as the conditions present in their interiors. It might also shed light on the processes that govern the formation of planets and stars. Metallic hydrogen is thought to play a key role in Jupiter's magnetic field, and analyzing it directly could help explain how such fields are generated and maintained. The logistics of mining Jupiter for metallic hydrogen would require international collaboration and unprecedented technological innovation. It might involve building a fleet of autonomous spacecraft capable of withstanding extreme conditions, or even establishing orbital stations around Jupiter to act as hubs for mining operations. Advanced robotics and artificial intelligence would likely play a crucial role, as sending humans into such an environment would be impractical, if not impossible. One possible approach to solving the problem of transporting metallic hydrogen might involve processing it on site, converting it into a form that is easier to handle and transport. For example, the hydrogen could be used to produce high-energy fuels or materials directly in Jupiter's orbit, reducing the need to lift large quantities of material out of the planet's gravity well. Alternatively, smaller quantities of metallic hydrogen could be extracted and tested, allowing scientists to better understand its properties and develop methods for handling it safely. The technologies developed to explore and mine Jupiter could have applications on Earth, such as improving materials, science, robotics, and energy storage. The effort could also inspire a new generation of scientists and engineers, much like the Apollo program did during the space race. The hypothetical Jupiter engine, using the gas giant as a solar system propellant. Jupiter could, in theory, be a key component in moving objects within the solar system, or even moving the solar system itself. This speculative concept draws from theories about stellar engines and gravity assists. offering a glimpse into how humanity, or an advanced alien species, might one day harness the power of the largest planet in our solar system. Gravity assists are already a cornerstone of modern space exploration. Spacecraft like Voyager and Galileo use Jupiter's gravity to slingshot themselves to higher speeds and new trajectories, saving fuel and time. These maneuvers are highly efficient because they tap into the planet's orbital energy. Scaling this idea up, it's possible to imagine using Jupiter's gravity to alter the orbits of much larger objects, like asteroids or even moons. By carefully timing interactions with Jupiter's gravity, celestial objects could be moved into new orbits, potentially allowing for the construction of vast megastructures or the rearrangement of resources across the solar system. Another theoretical framework that involves Jupiter is the concept of a stellar engine, which is a hypothetical structure designed to move an entire star system. One proposed type of stellar engine is the Shkadov thruster, which uses the energy output of a star to create thrust. While Jupiter itself isn't a star, its mass and composition make it an intriguing candidate for similar engineering on a smaller scale. A civilization could, in theory, construct enormous reflective structures around Jupiter to direct solar radiation or harness its rotational energy. By converting these forces into thrust, the planet could act as a kind of cosmic tugboat, nudging the solar system, or parts of it, through interstellar space. To achieve such a feat, however, would require overcoming significant challenges. Jupiter's immense size and mass make it an attractive source of energy, but they also mean that manipulating the planet would demand an unimaginable level of technological sophistication. The reflective structures needed to harness solar energy, for example, would have to be multiple orders of magnitude larger than anything humanity has ever built. These mirrors or collectors would need to remain stable in Jupiter's intense gravitational field, as well as withstand the planet's powerful radiation belts. Additionally, any thrust generated would have to be precisely controlled to avoid destabilizing the orbits of other planets and moons in the solar system. One possible way to harness Jupiter's energy without physically altering the planet would be to extract and use its abundant hydrogen and helium. These elements could be used as fuel for fusion reactors. Fusion power is considered one of the most efficient forms of energy generation, and if advanced civilizations could tap into Jupiter's vast reserves, they might be able to create propulsion systems capable of moving massive objects. By using fusion-powered engines, it might even be possible to build a system that directs controlled bursts of energy outward, creating a form of thrust that pushes the solar system incrementally over time. Jupiter's magnetic field also presents intriguing possibilities. If an advanced civilization could find a way to harness this magnetic energy, they might be able to generate propulsion forces or create protective barriers for spacecraft and other structures. The magnetosphere could also serve as a conduit for transmitting energy across vast distances, enabling the operation of systems far from the planet itself. A civilization might use Jupiter's gravity to guide asteroids or comets into specific trajectories, either to harvest their resources or to create defensive barriers against potential threats. By carefully orchestrating gravitational interactions, entire asteroid belts could be reshaped or redirected, transforming them into tools for exploration or defense. Altering the planet's natural state could have far-reaching consequences for its moons and the broader solar system. Jupiter's gravity and magnetic field play a crucial role in maintaining the stability of its moons, many of which are of interest for scientific study and potential colonization. Disrupting these systems could lead to unintended consequences, such as destabilizing orbits or altering the conditions necessary for life. Advanced civilizations would need to weigh the potential benefits of harnessing Jupiter's energy against the risks of damaging the intricate balance of the solar system. Such a project would require not only immense technological capabilities, but also a deep understanding of planetary systems and a long-term vision for the future. If humanity were ever to undertake such a project, it would likely represent a turning point in our evolution as a species. marking the transition from a planetary civilization to a truly interstellar one. The energy puzzle, tapping into Jupiter's magnetic field for advanced technology. Jupiter's magnetic field has sparked the imagination of scientists and futurists, leading to discussions about how advanced technology could harness it for energy or propulsion. Jupiter's magnetosphere is about 20 times stronger than Earth's at the surface, and it extends far beyond the planet, enveloping its moons and capturing vast quantities of charged particles. This region, filled with energetic ions and electrons, represents a colossal reservoir of electromagnetic energy. If humanity, or an advanced alien civilization, could develop the technology to interact with this field on a large scale, it might open the door to nearly limitless power. When a conductor moves through a magnetic field, it generates an electric current. This principle is already used in technologies like electric generators on Earth. In Jupiter's case, spacecraft or satellites equipped with long conductive tethers could be deployed within the magnetosphere. As these tethers move through the planet's magnetic field, they would generate electrical energy. The energy could then be stored in onboard systems or transmitted wirelessly to other locations. This approach, while theoretically sound, presents several challenges. Jupiter's radiation belts are unfortunately also some of the most intense in the solar system. Any equipment placed within the magnetosphere would need to be heavily shielded to survive the constant bombardment of high-energy particles. Additionally, the sheer scale of the magnetic field would require technology capable of managing and storing immense amounts of energy, far beyond the capabilities of current systems. However, advances in materials science and energy storage could make these hurdles less daunting in the future. Magnetic sails, a concept that has been proposed for interstellar travel, could theoretically be deployed within the magnetosphere. These sails would consist of large, lightweight, conductive structures designed to interact with the magnetic field. By generating controlled currents within the sails, a spacecraft could create magnetic forces that propel it through space. This form of propulsion would be highly efficient, requiring no onboard fuel, and could allow for rapid travel within the Jovian system, or even beyond. The field could also serve as a medium for communication or power transmission. Using advanced electromagnetic technologies, it might be possible to send signals or energy across vast distances by interacting with the magnetic field. This capability could enable the development of a planetary-scale energy grid, where power generated in one part of the Jovian system is transmitted to other locations, including bases on the planet's moons or even distant spacecraft. Jupiter's moons could play a crucial role in these scenarios. They lie within or near the magnetosphere, making them ideal locations for energy collection and storage. Ganymede, in particular, has its own magnetic field, which interacts with Jupiter's magnetosphere, creating complex electromagnetic dynamics that could be exploited for energy generation. Advanced technologies might use the interplay between these fields to harvest energy or develop novel propulsion systems. One of the most ambitious ideas involves the creation of massive orbital structures designed to interact with Jupiter's magnetic field. These structures, sometimes referred to as energy rings or magnetic collectors, would consist of enormous conductive loops placed in orbit around the planet. By aligning with the magnetic field and moving through it, these rings could generate vast amounts of electrical energy. This energy could then be used to power large-scale industrial operations, such as mining or manufacturing, or to support human colonies on the Jovian moons. Jupiter's magnetic field, combined with its abundant resources of hydrogen and helium, could serve as a refueling and energy hub for spacecraft traveling to other star systems. Fusion-powered spacecraft, for example, might rely on hydrogen extracted from Jupiter's atmosphere and energy harvested from its magnetic field to recharge and continue their journeys. This combination of resources could make Jupiter a central node in a future interstellar transportation network. While the field itself is a natural phenomenon, any large-scale exploitation of it would need to be carefully managed to avoid unintended consequences. For example, altering the dynamics of the magnetosphere could affect the radiation environment around Jupiter, potentially impacting its moons and any future colonies. Advanced civilizations would need to develop technologies and strategies that minimize these risks, ensuring that the benefits of energy generation are balanced against the preservation of the Jovian system's natural state. Jupiter as a natural particle accelerator. Insights into high-energy physics. Jupiter's magnetosphere is not just a powerful shield or a source of immense energy. It also functions as one of the most extraordinary natural particle accelerators in the solar system. The intense magnetic field, combined with the fast rotation of the planet and its interaction with the solar wind, creates a dynamic environment where particles are accelerated to extreme speeds. This phenomenon offers a unique opportunity to study high-energy physics in a natural setting, providing insights that are difficult or impossible to replicate in laboratory conditions on Earth. The magnetosphere traps particles from the solar wind, as well as those originating from volcanic eruptions on Io. These particles, primarily electrons and ions, become energized as they spiral along magnetic field lines, reaching velocities close to the speed of light. The process mirrors, on a much larger scale, what happens in human-made particle accelerators like the Large Hadron Collider. Electrons in the magnetosphere can achieve energies measured in tens of millions of electron volts, while heavier ions like protons can reach even higher energies. These high-energy particles generate intense radiation belts around the planet, which are far more powerful than those surrounding Earth. By studying the dynamics of these particles, scientists can gain a deeper understanding of the processes that govern particle acceleration and radiation generation in extreme environments. The study of Jupiter's magnetosphere also provides a space for exploring the behavior of cosmic rays. Cosmic rays are high-energy particles originating from outside the solar system, often produced by supernova or other energetic astrophysical events. When these cosmic rays encounter Jupiter's magnetosphere, they interact with its magnetic field and trap particles, creating complex cascades of secondary particles. Observing these interactions allows scientists to investigate how cosmic rays propagate through magnetic fields, shedding light on their behavior in other parts of the universe. The insights gained from studying Jupiter's natural particle acceleration extend beyond planetary science. They have implications for understanding astrophysical processes on a much larger scale. The mechanisms that accelerate particles in Jupiter's magnetosphere are similar to those thought to operate in the magnetospheres of pulsars and black holes. By examining these processes up close, scientists can test theories about how particles are accelerated in some of the most extreme environments in the universe. The radiation belts generated by the accelerated particles create a harsh environment for any spacecraft or potential habitats in the vicinity. Understanding the dynamics of these belts is essential for designing missions to explore Jupiter and its moons. It also provides valuable insights into the challenges that high-energy particles pose for habitability in other planetary systems. Spacecraft like Galileo and Juno have carried instruments designed to measure the properties of the magnetosphere and the particles it accelerates. These missions have provided detailed data on the energy, composition, and distribution of particles in Jupiter's magnetosphere, helping scientists to build more accurate models of how these processes work. Future missions could expand on this work, using advanced instruments to probe deeper into these dynamics. One of the most intriguing possibilities for future research involves the use of artificial satellites or probes to actively interact with Jupiter's magnetosphere. These spacecraft could carry experiments designed to inject particles into the magnetosphere or to measure the effects of controlled disturbances. Such experiments could provide unprecedented insights into the behavior of high-energy particles and the mechanisms of particle acceleration. They could also help to refine our understanding of how magnetic fields influence the dynamics of charged particles, a topic with broad implications for fields ranging from astrophysics to plasma physics. The high-energy particles Jupiter's magnetosphere accelerates can interact with the surfaces of its moons, altering their chemical compositions and creating secondary emissions that can be detected from a distance. By analyzing these emissions, scientists can infer the properties of the particles and the processes that produce them. This approach has already been used to study the interactions between the magnetosphere and the icy surfaces of Europa and Ganymede, revealing details about the composition and structure of these moons. The interactions between particles and magnetic fields in the magnetosphere can produce unique signals such as synchrotron radiation, which can be detected and analyzed to study the properties of the particles and the magnetic field. These observations can provide clues about the fundamental forces that govern the behavior of matter and energy in extreme conditions. Could Jupiter have sparked life on Earth? Jupiter has long been regarded as a protective giant, shielding Earth from potential cosmic impacts. However, its role in shaping life on Earth may extend beyond deflection. Some scientists propose that Jupiter's gravitational influence might have actively contributed to the conditions necessary for life to emerge on our planet. This hypothesis suggests that the gas giant played a key role in directing water-rich comets and asteroids toward Earth, delivering the building blocks for life. During the early formation of the solar system, Jupiter's immense gravitational pull acted as a disruptor, scattering smaller bodies across the solar system. Among these were icy comets and asteroids originating from regions like the Kuiper Belt and the Oort cloud. These celestial bodies contained significant amounts of water ice, as well as organic molecules, key ingredients for the development of life. Earth, in its infancy, was a molten and inhospitable world. The planet's proximity to the Sun made it unlikely to retain water during its formation. The intense heat would have caused any water to evaporate, leaving Earth dry. For liquid water to exist on its surface, an external source was necessary. This is where Jupiter's gravitational influence becomes crucial. By perturbing the orbits of water-rich bodies, Jupiter may have sent them hurtling toward the inner solar system, where they collided with Earth. These impacts would have been both catastrophic and transformative. As comets and asteroids smashed into Earth, they delivered not only water, but also a variety of organic compounds, including amino acids and nucleotides, the building blocks of proteins and DNA. Over time, these materials accumulated, creating a primordial soup rich in the chemical precursors of life. The energy from these impacts, combined with the planet's evolving conditions, could have triggered chemical reactions that eventually led to the formation of simple life forms. The late heavy bombardment, a period of intense asteroid and comet impacts approximately 4 billion years ago, is often cited as evidence of this process. During this time, Jupiter's gravitational influence may have been particularly significant. By perturbing the orbits of objects in the asteroid belt and beyond, the planet could have caused a cascade of impacts on the inner planets, including Earth. These collisions not only delivered water and organic compounds but also created temporary habitats, such as hydrothermal systems, where life could have originated. The hypothesis that Jupiter played a role in jump-starting life on Earth is supported by evidence from meteorites. Some meteorites that have landed on Earth contain amino acids and other organic molecules that are not found naturally on our planet. These materials are thought to have originated from asteroids and comets that were influenced by Jupiter's gravity. Their presence on Earth suggests that similar materials may have been delivered during the planet's early history, contributing to the chemical diversity needed for life to emerge. Observations of other planetary systems reveal that giant planets like Jupiter are relatively common. However, their positions and movements within their systems vary widely. In some cases, giant planets migrate inward, disrupting the formation of smaller planets and making the system inhospitable to life. In others, they remain at a distance, creating stable environments where smaller planets can develop. The specific position of Jupiter in our solar system combined with its gravitational influence, may have been a key factor in creating conditions favorable for life on Earth. The same gravitational influence that directed beneficial impacts toward Earth also posed significant risks. Large impacts could have sterilized the planet, wiping out any nascent life. Balancing this risk with the benefits of water and organic delivery is a delicate equation, one that highlights the complexity of Jupiter's influence on the early solar system. If giant planets play a similar role in other planetary systems, they could increase the likelihood of life emerging on other worlds. Observing exoplanetary systems with configurations similar to our own may provide insights into the conditions that favor the development of life. Jupiter's contribution to life on Earth is not just a story of the past. The planet continues to influence the solar system, shaping the orbits of comets and asteroids and occasionally sending them toward the inner planets. These ongoing interactions remind us of the dynamic and interconnected nature of the solar system, where even distant giants can have profound effects on life-bearing worlds. And on that note, this video must come to an end. What other idea would you like for us to cover next? Comment down below if you'd like a similar video for another planet, and if you enjoyed this one, consider leaving a like and subscribing. Thanks for watching.